on week 4. So let's wait 1 minute and we will start. So my screen is visible, right?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So yeah, it's now time to start the session. So to start session, first I want to say uh, we will not discuss about the bonus marks or expression kind of queries, because those things have already many times have discussed what is the bonus mark and how. So I will not going to introduce such kind of questions. We will only focus on the week 4, and also we will cover in the sense if you have doubt, because this is an open session. So if you have doubt on week 3, week 1, week 2, whatever you have doubts, we can discuss those. So we will only discuss the content kind of question. We will not discuss about or any kind of operational kind of queries like marks or some question type or bonus marks, something. We will not going to discuss this. So you can start your asking your doubt.
Sir, actually, I thought today was the solve with us session. So,
No, today is actually open session. Yeah, if you like, if you think that some question like activity or practice assignment kind of till now, we can. This is open, so we will discuss those also. Okay.
okay, sir.
So, like I am introducing the week 4 contains is about basis and linear independence, dimension, basis.
Sir,
Basis.
I have a doubt.
Okay, dimension.
Yeah,
Okay.
sir. Sir, according to me, if 2 points are in a plane in of R square, then they are linearly dependent if 1 point, sir. If
2 points.
1 point, no,
2
only
points.
only one.
Okay, if there is only 1 point in R2, okay.
Yeah, sir. Suppose no, 2. If there are 2 points in R2,
Okay.
so that the line generated by them, if it is not passing through origin, then they are linearly independent or dependent.
Just 1 minute. Yeah. So yeah. Can you repeat again? Actually, 2 points are there, and they are like what you said.
Yeah, sir, मैं एक बार can I speak in Hindi?
Yeah, you can.
या सर क्या कहते हैं, अगर हमारे पे कोई प्लेन है आर स्क्वायर, उसमें मेरे पे कोई एक पॉइंट है मेरे पास, तो उस पॉइंट से जो लाइन पास होती है, अगर वो ओरिजिन से पास हो रही है, तो वो लीनियरली डिपेंडेंट वेक्टर्स होते हैं. नहीं, वो सब स्पेस होता है अगर उस वेक्टर स्पेस का, अगर हम आर स्क्वायर में देखें. और अगर हमारे पास 2 पॉइंट्स है कोई, और अगर वो लाइन से ओरिजिन से पास नहीं होती, तो सर वो वेक्टर लीनियरली इंडिपेंडेंट होंगे या डिपेंडेंट होंगे?
Okay. So पहले like if I will say 2 vectors, like not vector, the thing is talking
Points.
about linearly independent or dependent. we need vectors. There is no such kind of lines or passes through. There is no such concept.
Okay,
We
okay.
talk about two vectors means if in R2, if we are in R2, so 2 points will be like coordinate wise A and B, like C and D. So these
Yeah.
are like R2 is a vector space with usual addition and scalar multiplication. So these two vectors, like these point now we will call as a vector. Now these
Okay.
two vectors are linearly independent, like talking about a linearly independent or dependent. Those things are related to only vectors, not like passing through a line. Or if
Oh,
you talk about, if your question should be like there are two vectors in
yeah.
plane here
Actually,
and
sir, I I am not able to say my question in proper way. Actually, I am trying to say that how can we realize geometrically
yeah,
what is linearly independent and dependent
yeah, okay,
such
okay,
such
yeah.
things? Yeah.
So yeah, let me explain that. Yeah. So yeah, that's the mean of, if we talk about the geometric meaning of linearly independent, then the word came in R2 as a line.
Oh, yeah.
So as see, like I am taking 2 vectors in R2, like 1 2 and 2 4. Okay.
Okay.
So these are 2 vectors. Now first things, how we will check these 2 vectors are linearly independent or dependent.
Yeah, sir. We will multiply by two scalars and put equals to zero vector.
Yeah,
And if A and B are zero, then they are linearly independent.
yeah. So let's check that. This will be A plus 2B is equal to 0. Coordinates why
Yeah,
they
yeah.
will be
Addition.
equal. So
Hmm.
the 0 means 0 0, and the second is 2A plus 4B is equal to 0. Now if you see that the second equation, now this is a system of linear equation and you have to solve this. So now in the second equation, if you observe, if you take common, it will be A plus 2B, which is equal
Yeah.
to 0, implies A plus 2B is equal to 0. The same first equation.
Yeah,
So
sir.
you can write it as A is equal to minus 2B. That means there are so many possible A values of A and B such that this can be 0, this linear combination. This is called the linear combination.
Yeah, sir.
So that means these two vectors are linearly dependent.
Okay,
Okay.
sir.
Now,
Yeah.
what it mean by the like saying to be geometrically these two vectors are linearly independent or dependent. So, like if you see that actually this is, you know that this equation in R2 represent a line.
Yes, sir.
Like it will be some uh, it will be A minus 2B. It will pass through 0. Some it will be like this because A is equal to minus 2B. Okay, just 1 minute, 1 minute. So
Sir, my doubt is that is a linear combination of vectors is also a subspace of V?
no, linear combination, like subspace is talking about, subspace is nothing but a vector space,
Yeah,
but
sir.
it will be subset of R2. Or maybe that there
Yeah,
will be a superset which is
yeah,
also a vector space.
yeah, सर अगर हम ज्योमेट्रिकली देखें, अगर हम आर स्क्वायर में एनालिसिस करें
Hmm.
तो हमारा आर स्क्वायर पूरा वेक्टर स्पेस मान लें अगर हम, तो
Hmm.
उसमें जो हर लाइन होगी जो ओरिजिन से पास हो रही होगी वो उसका
हाँ,
सब स्पेस होगा,
वो सब स्पेस है.
क्योंकि जीरो वेक्टर कंडीशन जरूरी है उसमें आने के लिए.
Yeah.
बट
Zero should be that. So it should
हाँ,
pass to area.
बट अगर वो जीरो वेक्टर से पास नहीं हो रही कोई दूसरी लाइन तो वो
हाँ.
सब स्पेस होगी या नहीं होगी?
No. So अगर वो जीरो से पास नहीं हो रही है तो इसका मतलब उसमें जीरो वेक्टर है ही नहीं.
ओके,
और
वेक्टर स्पेस की कंडीशन नहीं
तो
फुलफिल
वेक्टर
कर ली.
स्पेस, सब स्पेस का जो कंडीशन है और वेक्टर स्पेस के जो कंडीशन उसमें फॉल ही नहीं कर रहा है, तो वेक्टर स्पेस सब स्पेस नहीं होगा और वेक्टर स्पेस नहीं होगा.
ओके सर.
So
So I mean, it should pass through 0, 0. I mean,
Sir,
if we have to check for a subspace or a vector space, like we do linear combination as you did.
yeah, correct.
So we have to equate it to 0, 0. I mean, to check if A and B also are coming 0, then we can say that it is a subspace of the main vector space, or it is the
No. Sorry. No. Checking for
checking for.
subspace is You are saying to be checking for subspace, right?
Yeah, subspace, sorry.
So to checking, let me go here. Okay.
Yes.
So checking for subspaces, there are three conditions. The first condition is right.
To check for subspace.
Yeah. Okay, just a minute. So fine. Okay, no, I see. Yeah. So there are three conditions. The first condition is 0, 0 or 0 vector. First is like let me take a vector space first. Like talking about the subspace means there should be a vector space, and we will check there, and there is a subset of that vector space,
space.
and we will check that these three conditions for checking subspace. There is three condition. We'll
Yes.
check that is that subset follows those condition or not. So first is that needed, we need a vector space. So let's say I am taking a vector space R2. Now I am taking a subset. Let's say yes is that such that the elements from R2, okay, the following the condition x plus y is equal to 0. The coordinate relation is x plus y is equal to 0. Okay.
Yes.
Okay, sir.
So this is the subset of R2, which is a vector space. Now, is this subset yes is a subspace or not? So for the checking subspace, it will take the operation, whatever the operation this here R2 have, which is coordinate wise addition and coordinate wise scalar multiplication. With respect to those operations, this follows the first condition. 0, 0, 0 vector is in the set or not. 0 vector. The second thing is, if we take two elements from this set, let's say A means A will be like coordinates y. Let's say I am taking x1, y1, and let's take another element which is B, and
Sir,
which is
yeah, sir, this zero vector is the I think okay, ये जो zero vector है, ये इसकी additive identity को show करता है.
Yeah, actually zero vector is saying to be additive identity.
क्योंकि field और ring की definition में वही होता है. Vector space में zero vector आ जाता है.
Correct. Okay. So take two elements from this set, yes. Now it should follow A plus B. If you add with that operation which is in R2, it should belongs to yes. And the third condition is take again a element A, which will be in coordinate wise, and take a scalar with there. If there will be a vector space, so vector space over R, writing to be like a scalar field we needed. So for this course, always we are taking a
Real
field.
number, right.
This scalar field is real number. So C belongs to a real number.
Okay,
now,
sir. We have to check it consists zero vector. It is closed under addition.
And it should close
scalar
under
multiplication.
scalar multiplication.
To check for a subspace.
To check for a subspace. If these three conditions followed by yes, then we will say this yes is a subspace.
Okay.
Okay.
But sir, in this, if
so can you take some examples like coordinate example to explain because you mentioned like x plus y equal to 0. So when we do the addition, right? So a plus b should be element of subspace. So
Yeah.
how will it maintain that condition, sir? I just want to understand that.
Yeah. So let me show you that how it's happening. So A is x1, y1, and B is x2, y2. Now
so can I say that on the plane R square, the line the equation of line where x equals to minus y is the set is the subspace of this condition?
Yeah, actually this is a subspace. We will check this.
Okay.
So let's check. I have added this A plus B. So it will be x1, y1 plus x2, y2. Okay, A is x1, y1, B is x2, y2. So addition is coordinate wise as in R2. So let's add here addition as a coordinate wise y1 plus y2. Now just a minute.
So this must be 0, right? As per the rule.
Yeah. So as for we took two elements from yes, A and B. So it should follow this one. X1 plus y1 is equal to 0, and this should also follow x2 plus y2, because taking two element means taking an element means it will follow this condition. Then it will be like in this set, right? This will be an element of that.
But sir, when we are adding x1 and x2, will it be 0?
Yeah, actually, see, I said here A is an element from S. What it means that it should follow this condition, then it will be an element, right?
Yes. Yes.
Sir, in R2, can there ever be a unique zero vector that is not the origin or 0, 0?
So no. Can you repeat again?
Can there ever be a unique zero vector which is not the origin, say in R2 0, 0? Other than that,
Yeah.
can there ever be a unique
Actually
zero
there
vector?
can be possibility, but yeah, operation will be different. When you change the operation plus, like, let me define the operation like this. In
Sir,
art,
if
let me
multiplication and addition are given, then we
here
consider
is
it.
the addition is like a coordinate wise happening. If you change the addition operation different, there are possibility where the addition will be different. Like defining is like this is, but the operation, let me show you an example. Like I am taking
like sir in
that
vector space activity questions.
And in some specific condition like self-defined addition or multiplication, then it can also have a unique non-origin zero vector and also qualify as a vector space depending on what is
what are the conditions are there, like
Yeah,
8 conditions should
zero
follow.
vector may change. It won't be 0 always as
Yeah.
per the operation, and there will
Sir,
be a
can you-
unique zero vector, right? So in
Yeah,
the
So
yeah,
can you
correct.
give an example of a non-zero unique vector?
Non-zero, like different from 0, 0. Yeah, I will
Yes.
give one example. So
Please.
first let me finish this.
Yes,
Somebody
sir,
is
please
waiting.
complete. Sir, let's not
Yeah.
disturb the flow, sir. You can continue, sir, please.
Yeah, let me finish this, then we will be back to here. Okay, so the A is an element of S, so this should follow, and B is an element of S, so it will follow this condition. Okay, then it will be element of S. Now when we added here, the operation is coordinate wise, so coordinates wise we added. Now we have to check this when we add these two, if like here, if we want this element, now this is a single element, right? This is one coordinate, this is one coordinate. Now this is a single element, so this is a single element. If we want this is an element of yours, so what we need to check here, this is one coordinate and this is another coordinate. We have to add and check this should following or not. When it will follow, we will say yes, A plus B an element of this. So let's do here the coordinate wise. Here it says the coordinate wise addition, like no, not coordinate wise. The first coordinate is a second coordinate added, and it is as a 0. So here as it is. So this is the first coordinate and added with the second coordinate here. So as now we have to rearrange this. Like if you reach it here, like x1 plus y1 plus x2 plus y2. So we have a condition x1 plus y1 is equal to 0. So that means this is 0, this is 0.
Sir,
So
x1 plus y1 is 0 by definition, actually, as we are taking a point, taking the vector from that subspace.
Yeah, because we are taking the element from here. Yes. Okay. So that means when we added here, we got this element, and when we got this vector, and when we check that these coordinates, when we added these two coordinates, is make 0. Yes, that means this vector belongs to here. Yes, that means this addition is belongs to here. This after adding these two vectors, we got a single element which is an element of this. So that means the addition, like when we added, and the second condition followed by yes. Now next we have to check the third condition, which is scalar time multiplied with a vector. So again, A is a vector, that means A is
Excuse me, sir.
x1 y1. Yeah.
So first condition is true, zero vector.
Yeah, zero is we jump to here. Okay.
Hmm.
I will back to here. Okay. I
Okay.
will back to zero vector. We will check.
Hmm.
Okay. So now let's check for third condition, which is again we are taking a as a x1 y1. So again a is element of s, that means x1 plus y1 is equal to 0. Now when we multiply it with a scalar with this vector, it will be c dot a, c times a, that means c x1 y1. So multiplication with this is applied as a coordinate wise. So c times x1 comma c times y1. Now we got when we did this operation scalar multiplication, we got this vector. Now this vector is belongs to yes or not. We have to check this condition. Uh, this is following or not. Coordinate wise addition, like not coordinate is when we add these coordinates. Yeah, okay. So let's add this cx1 plus cy1. We can make it as cx1 plus y1. And we have already as said this followed by a, that means c times 0, which is 0. That means c dot a, this vector belongs to s. So that means this is scalar multiplication with a vector followed by s. So these two conditions followed by s. It still remains 0 vector. So let's check 0 vector. So 0 vector is there 0 vector or not? So how we will find the 0 vector in that? What will be the 0 vector? So let me tell you, whenever there is a subspace, then we will say
Inverse
okay,
of it
maybe
there exists. Inverse exists.
no. Okay, let me tell you.
Yeah, sir. V plus 0 equals to V. The operation.
Let me tell you how it's.
Yeah,
Let's
please,
assume. Let's assume like 0 vector says, okay, I am taking a vector from S. I am supposing V is. I am saying V is 0 vector. Okay, just 1 minute. I am taking V is a vector. It's happening like A plus V is equal to A. Because we want V. Actually, we want to try. We want to find V. Okay, we want to find V. I am assuming like whenever you solve a problem, you used to assume yeah this is X. So I am assuming V is a X, like V is a vector when we added an element with an element of S, it gives this. Okay. So now I have assumed let's A is A1 A2. Okay, I just these are the parameters. So I am assuming A is A1 A2 and V is let's say V1 because V means because this is I am trying to find a 0 vector from S. So assume we want to find the element from S. So it will be coordinate wise, like in two coordinate, first one and second one. Now when we added here, it will be A1 B1. We are trying to solve this equation when we
A1 A2 no.
Yeah A1 sir.
Not
A1.
B1.
A1. So that means when we added now coordinate y, let's add it. So it will be A1 B1 and second one is A2 plus B2, which is equal to A1 A2. Now let's compare here. A1 plus B1 is equal to A1. A2 plus B2 is equal to A. You can cancel out. That means you got here V1 is equal to 0 and here V2 is equal to 0.
So, sir,
So that means you obtained V 0 0. That means V is 0 0.
Yeah, sir.
Now
That
let's
means
check
0
the
vector
conditions.
exists in this subspace.
Yeah, actually, this is the process to find 0 vector in a subspace or in a vector space. This
sir,
is the
can you show an example where the zero vector is not there in a subspace actually?
Yeah, I will tell you. Yeah, I will tell you. Okay.
Yeah.
We are assuming that by adding A to B, we are getting A. First, this is assuming, right? Assumption. This is getting.
We will also see that. We will
Okay.
actually find that there is no 0, 0. We
Hmm.
will reach
Yeah,
there.
sir, for this we have to define the addition and scalar multiplication according to that process.
According to what see,
Yeah.
if there is a question, surely operation will be given. Without
Two operation.
operation, how you will say, what we will check in that? We will check according to the operation and those conditions. So if someone is asking that if yes is a set is a vector space or not, so you will ask that what is the operation you are giving? Please tell me operation. So he will tell you, okay, do this operation. This is the plus operation, and this is the dot operation or multiplication operation. He will define the operation, and then you will check the eta of C.
But sir, if equation is giving, then also the possibility that the vector 0 is not present on that equation.
Yeah, actually, let me finish then I will tell you. Okay.
Okay.
So yeah, actually, so you find 0, 0 in that. So that means 0 vector is in yes. Actually, when you add this coordinate a plus, so means 0 plus 0, which is 0, which is follows that 0, 0 when we added coordinates here. So we got 0 in right side. That means 0 is in yes. So yeah, yes is a subspace.
Just one question from that third point, where A plus B was telling that that previous third point actually.
Okay.
So x1 y1 is at one point and x2 y2 is another point. Is fine. You are adding, and after that you are showing that x1 plus x2 plus y1 plus y2, and this, where is this plus coming from actually?
No. So see, this is, see, when you added these two vector, you added the coordinate y. So this is a vector. This sorry, this is a single coordinate. This is a single coordinate, right?
Yes.
In a, so this is a single vector where these two coordinates are here.
Oh, so we are adding those two coordinates.
These two coordinates we added, as here the condition is that these two coordinate and these two coordinates are added. Then we got 0.
Here, sir, standard multiplication and addition condition are giving in coordinate, like in coordinate geometry.
Here is a standard, that's the usual addition and scalar multiplication. That's the car.
Basically, we are adding the coordinates to form a vector of C times x1, y1.
Can you please tell me why we need not to check the other eight properties that we have?
Actually, when you check this 8 property with one by one yes itself, you will say that these 3 is enough to tell those.
Subspace is enough to check for two properties.
Yes, sir, there are lot of theorems and lemma for that.
For that there are some theorems which says that only checking these 3 is enough to say this is a subspace.
Because the subspace is comes from vector space, so all the properties of vector space will satisfy the subspace, and we have to check for only these two.
Correct.
Rest
all are inherent
all
of
are
this.
Inherent, yeah.
When we have
inherent of this
vector space, we have to check all axioms, right?
If there is no like saying checking for vector space, for that you have to check all these 8 conditions. Okay, so let me replace here 0 with 1. Only slightly I am changing here. Okay. Now this is a different yes. Okay. Now this is a different set, right?
Yes.
Before that, when we added coordinate, we got 0. Now this is a different. This is a different set from that previous one where it was 0.
Is
now
this a vector space?
Now again the question. Yeah. So let me finalize this. This is not a subspace of that vector space R2. Okay. So we will check that why this is not happening.
Sir,
the two properties satisfied, right? The addition and the scalar.
Actually these two will satisfy. 0 is not in there.
Yeah, sir, we can predict by analysis also. If I take y equals to minus x plus 1 and 0, 0 is not satisfied by this equation, that means the line is not passing from origin. So that it is not a subspace.
That's the meaning of. That's
the
meaning.
Could you give an example where it is a vector space?
Sir, can we go through
non-zero?
I think sir can take us through the step, no? X plus y.
Yeah, you can check for the example. I mean,
because this
Yes.
is not a subspace, but we just want to see a vector space where it is a non-zero.
Yeah.
See, sir is going to take us through that.
No. Vector not a that if the zero is not
Subspace.
in that will be never a subspace
Vector
or
space.
vector.
No,
Will not-
actually not a subspace. I'm saying if a vector space, is there a vector space with non-zero coordinate?
No, actually there is no vector space.
Non-zero coordinate.
No, non-zero. If there is a vector space, zero should be in that.
No, zero,
vector.
but not zero is not the zero. Without
So that is
Okay.
I have written here. My question is here. I will show you apart from 0 there is a zero vector. I will show you. Okay. I have written that question. I will show you.
Right.
So let me finish this.
Okay.
So actually now this set is changed from that previous one. This set yes is different from that previous one. Okay. So now again, if you check each, let me jump to here. If you are here from the starting, so that means if A is a set here, sorry, A is an element of that set.
Can you clear the screen and start, sir?
Condition follow that.
Can you clear the screen?
Here will be 1. X1 plus Y1 will be. Okay.
So can you clear the screen and just start? Take the example x plus y equal to 1. Clear the screen and do it so it will be clear.
Actually, I want to tell you same thing. Only what are the differences? As here, I am not cleaning this because you will get the same thing. Same means you will see the differences. What is happening? That's why I am not erasing whole. Okay.
So please use different color then, sir.
Okay. Okay. Yeah. Let me change the color. Let me change the color. So okay. So okay. The previous one was 0 here. Okay. Now yeah. So this is this one is now here. Yes is different. Now again we will take A as element. Again as same x1 y1, but this A is, and I am saying an element, that means coordinates. When we add these two coordinates, it will give 1. As previous one is 0, it will be 1. Okay, because as here the condition says. Okay, now I am taking another element P, x2 y2. That means it should again follow the condition x2 plus y2 should be 1, as I am saying B is an element of S. Okay, now let's add here A plus B. So again coordinate wise addition will happen as here. Okay, so now this is an one coordinate, this is an another coordinate. So let's add these two coordinates as I added here. Okay, so final thing again, you just rearrange the term, find the x1 y1 as here, x2 y2 as here. Okay, now when we added here, this is 1. Okay, this is again this is 1. So that means when you add here, we obtain here 2.
So it's not a vector space. It's not a vector space. No.
See,
it is not closed under
go
addition.
0 0. This itself says that this element is not from this set. Yes. Why? Why I am asking from you why this is happening.
Because sum of 2 is 1. And
yeah, actually reason is when we added these two coordinates, when you added, we got 2, not 1, as here the condition says. It should be 1, but when we added here, this is a coordinate, first coordinate, this is second coordinate. When we added these two coordinates, we got 2. Because of this reason, as here x1 y1 we rearrange.
So you mean that x plus y there was 1, and here you are getting as 2.
That means A
so 1 is not
B
equal to 2.
Element of S. That means when we are getting, that means this element is not. When we added, that means this when we obtain this element is not from S, because when we are adding the coordinate of these two, it's happening, we are getting 2, it should be 1.
Okay.
So that means this addition is not happening. Let's back to here, as we came after we did here like this, and we got Now back to here. That means this operation, this addition is not true for yes. So there you can say this set is not a subspace.
2 is not equal to 1, right?
Okay. So you can see that, yeah, you can here observe. So that's the process. Always if there is someone says checking for subspace, just check that these three condition is enough. If you single element, if you take directly itself, you no need to go here 0 0 0 0 itself tell is there possibility or not. As actually,
Sir, can there be no
R2
subspace for a vector space?
Sorry,
can there be no subspace for a vector space?
Is it possible?
Yeah.
No.
Possible.
For each vector space, there is two fixed subspaces. Now
One
I
is
want to ask
zero and other is the
line passing through
itself. Other it's the itself. Like zero
zero and
is
the
zero,
itself.
Zero and itself, because
zero
zero
and
is
line
also a subset.
zero line passing through zero and itself is R
Yeah,
square
actually,
itself is subspace.
not
Yeah,
line
vector
like V is. I am saying V is a vector space. So always it have at least two subspaces. What are those? Zero subspace. Zero subspace
Zero
means,
vector.
see, we have a zero vector. So take that zero vector and make a set. So this is actually, if you take whatever the operation we have, if you check all these three conditions for zero was only for single element zero, it will follow and it will form a subspace. So that means zero subspace. This is called zero subspace. And V is also subset of V itself, right?
Yeah.
Yes.
So that means if you check for that means checking for this operation as 3 itself, you will check. So V will follow. That means V is also subspace of itself.
Sir, I have a doubt. Can R2 can be a subset of R3?
Subspace, yes.
Yeah, because all the lines which are crossing the origin and all the planes which are crossing the origin are the subspace of R3.
So first, let me. you will tell itself. Is that R2 is subspace of R2 or not? So let me tell you. So I'm asking from you. R2 means an element of R2 will be coordinates wide, where will be 2 coordinate, right? And R3 means if there is a vector, it will be in 3 coordinate.
Yes.
So is this happening? Is
No.
this one is like this?
No, sir.
No. So actually R2 is not itself, like R2 is not subset of R3. So how you will say?
Yes, exactly.
It is not itself subset of R3. So how you will say R2 is a subspace of R3? To check, yeah, if that subset is not like subset, if you are wording it subset, that means it is going to be element from R3. But here R2 is not subset of R3. How then? There is no matter of checking these three conditions.
Here R2 and R3 are adjoint,
different,
right? Yeah.
What do you mean by adjoint?
I mean, they don't have any common.
No. So no, don't use. Actually, there is no adjoint kind of thing till for this course. Okay.
Sir, he meant disjoint.
Disjoint.
Disjoint. Yes, sir. Disjoint. Yes, sorry.
Sir, here x plus y equals to 1, you said, right? So there won't be any zero vector, right?
Sorry, which one?
Here, can you go up a bit?
This one.
A little bit. X plus y equals to 1 here. Here there won't be any zero vector, no? If x and y equals to 0, then both will come as 0, no? Addition
so
of
actually no actually there is no zero vector. Yeah, actually for this, this is not a zero vector. So let me tell you what's happening geometrically here. You will always look, while looking you will say no, this is not a subspace. The reason I am telling you, as in R2, as you studied in math 1, R2 is like as a coordinate wise system, right? Coordinate plane coordinate system, as you know. So R2 can be saying to be R2 with to be vector space with usual addition and scalar multiplication. Means usual addition means coordinate wise, as in coordinate system. Adding as a coordinate system, and scalar multiplication means multiplying a scalar with as coordinate wise. So R2 with usual addition and scalar multiplication, nothing with a coordinate system. Okay, so this is a coordinate system. Now I am writing here, yes, the first yes I am writing here. Let's say this is prime, and the first yes I am writing x plus y is equal to 0. Okay, so this whole, now see, this is R2 means 2 coordinates. So I am called, this is x-axis, this is y-axis. So this is, suppose this is whole R2. Okay, this is whole R2. Now yes, I am taking a subset of R2. That means this should follow the condition. So what are the points in S? The points will be
along the line y equals minus x.
Yeah, around means which will follow this equation. That means x is equal to or y is equal to minus x. So let's back to here our coordinate system. This line represent. Okay. So actually, that's why it's happening. This set is as a subspace because it's parts true origin. Now let's come to here our this one.
So it must
will be a subspace,
right?
if it passes through the true origin, right, sir?
Sorry?
It will be a subspace if it passes through the true origin, right?
Origin.
Yes, okay.
Okay. So
because it has to include the 0, 0 point,
0,
right?
0, correct. 0 vector.
Yeah, got it.
Now let's find the geometric interpretation of this S prime. So S prime is actually mean of this this after this vertical bar line. This says only the meaning of this equation, and actually this equation is in R2 is a line. This line x here, suppose this is 1, 0 and 0, 1. So hope you know that how to draw or which line is this. So this is actually, this S prime is, can geometrically you can say that this is S prime. So this is S prime. So now this line is not passing through origin. So directly you can say this is not a subspace. This is S prime. This is a subspace, but not a subspace. This is S prime. Now I am giving an example. Now whatever I told you, I am giving an example, and I will ask this set is subspace.
So subspace with reference to R2 you are saying, right?
Subspace
General
with
R2.
respect to R2. Yeah.
Okay.
So I am taking vector space R2, okay, with usual addition and scalar. So with respect to usual addition and scalar multiplication, I am defining a set A, which is defined like xy, okay, and 2x plus 3y is equal to 1 by 2 A. Now I want to say, I am asking from your side that this A is a subspace of this vector space V, which is exactly R2 or not. Now tell me.
No, sir. It is not,
sir. No, sir. Because zero,
it is not.
It doesn't satisfy the condition of zero vector. If I take x equals to 0 and y equals to 0, it gives halves.
But sir, apart from just straight away putting 0 and 0, because we are defining here the vector space. So I think blindly, if you're always looking at origin and trying to equate, so and a vector space 0 could be completely different from the origin, right? It need not be the origin. The vector, zero vector, sorry. The zero vector for a vector space need not be the origin. So
need not be origin, but yeah, but
yes,
it depend on the operation, whatever the operation.
Yes,
I still remain, my question is here. I will back to here, but I just want to with the usual addition and scalar and multiplication.
Yeah, sir, can you go up, sir?
Yeah, I will tell you. I will surely tell you. I will. Now it's time to reach that question. So So what is the reason? Directly you can say this line is not passing through origin, so that this is not a subspace. So I hope now directly, as whenever somebody is asking with usual addition and scalar multiplication and give a subset and ask is that subspace or itself say vector space or not, with usual addition and scalar multiplication. Okay. If somebody
for
is
this
asking
to be a vector space, sir, we just have to modify the vector space for characteristics of the vector space of R square over R square. Means if we say that the zero vector is half comma zero, like that, half comma half, we can say that, right?
We cannot say because the vector space is already defined.
No. So actually, that's why the operation. Always I am saying operation. Please consider the operation. Operation says coordinate-wise addition and coordinate-wise scalar multiplication, which is called usual addition and usual scalar multiplication. So,
sir, in the plane of R square, this subspace is given by the lines which are passing through origin. If I seen it as geometrically. So, sir, in three-dimensional plane, there are some lines which are passing through origin. There are some planes which pass through origin.
So, yeah, I will tell you R3. I will back to R3 also. I will back to R3 also. So let me finish this. So I hope you, all of you, that whenever somebody is asking that, let's say I am again giving a set that b is equal to xy such that 3x plus 5y is equal to, let's say, 5, and said b is a set and defining operation usual addition and scalar multiplication. Okay, is that B is a vector space or not? Okay, is B is a vector space or not?
Okay.
So you could directly, you can directly say that no, this is not a vector space.
How? Because zero vector
zero vector doesn't exist for it.
Yeah, because of this operation, as usual addition means coordinate wise saying, and coordinate wise saying means what it means that you can think this is a subset of R2 and think it as a subspace, and this subspace not passing through origin. This line is not passing through.
So my query is that, sir, we are taking this origin and trying to decide everything. So what I am saying is, unless and until we take example like, let's say, x1 y1 and x2 y2 and apply this to arrive at what is a zero vector, to know whether a zero vector exists for the space, we will have to do that step now, sir. We are just simply
you have
x
to
and y.
step. Yeah,
We can't simply put the origin x0 y0 and say zero vector. Origin is not a zero vector, so this is not a space. I say we have to have points taken. We have to consider two different values, apply here and see whether there is a zero vector or not.
Yeah,
right?
Yeah, but
you can't simply put 0, 0 on x and y and say
actually,
that,
it
see,
depends on usual addition.
This exam is as a giving as a 4 option.
Second, this
is not a writing like subjective kind of exam. So that's why I'm saying as a trick. Otherwise, it's your wish if you want to go with the procedure.
No, that's what,
sir, can I elaborate this concept?
Can 1 second? Can I come? Sir, can we take one point? Let's say x1 y1, assuming that x1 y1 is there. X1 y1 is a vector space. A vector in this space B, and assuming that zero vector is AB, and try to find out whether zero vector exists. Can we do that, sir?
We should be able to put x and y as 0 and the quadratic sum should come.
Sir has done previously.
Sorry, sir. 1 second. That's my point. I think simply taking the origin as a defining criteria for a zero vector, whether a vector space is existing or not, may not be. It's very limiting. I don't think it's the right way.
Actually, this is a limited. Yeah, actually, this is a limited. But actually, when you reading the question, please note with the operation. Okay, please note with the operation. If the operation is not usual, this will not happen. Okay, this may be a service.
Can you mute, please?
Please everyone mute yourself. Please.
Sir, my question is zero vector should also. So for zero vector of a vector space should also satisfy the operations, right?
Sorry, can you repeat again, please?
A zero vector for a vector space, if it let's say zero vector exists for a vector space, so it has to satisfy the operation, right? Zero vector also.
Yeah, actually, that's the main of. Yeah,
Okay.
Okay.
So why is this B
Yes,
not
sir,
a
to extend on that, if we put x1 as 0 and y1 as 0 and do the usual scalar multiplication and scalar addition, and if my answer comes as 0, then we can directly say the 0 vector exists. Right?
But how can you take 0? How can you take 0? If 0 vector, we have to check that it exists, and we have doesn't check that, and we
To check if it exists or not, so let's say 3x1 plus 5y2 as written on the equation. So if we take that, then put x and y as 0, and
No,
as
you cannot put 0 here because 0 is not defined yet. Because
Not
we are
always we
finding
can put
that this
0.
x and y belongs in our, it's defined. Yeah?
No, it is not defined. We are not finding whether it is a subspace. We are finding whether this itself is a vector space or not. So it could have a different 0.
Excuse me, sir. So I have a question.
I'm not understanding. So can you explain this?
Shubham, sir.
Yeah, I'm listening to whatever
Yes,
you are saying.
I think what sir
Please
told is
explain the
whether B
relation
is a
between
vector
determinant
space.
and linear dependence.
Yeah, sure.
Yes, sir.
Yes, sir.
Please.
So, okay. So, okay. Still, my question here is I have noted here. This is different from 0, 0.
Yeah.
I will back to
this.
Yeah, or okay. Let's finish this one. Then we will go to the linearly independent.
Yes.
Sir, when we will discuss week 4 content, sir.
Okay. So many of you are asking from here. That's why. Otherwise, I will directly jump to. Okay, I am leaving this one. And I'm
yes, sir. Week 4 actually.
Yes, sir, week 4 is main.
Sir, week 4, sir.
Okay,
Yes, sir. Week 4.
Sir, one example.
We have discussed this
You can just give
also.
for that.
Sir, this is a solve with a session
have to
for
do
week 4
graded, sir.
graded assignment.
Sir, but this concept is really a bit confusing, and I think many of us are not clear in that, sir.
Yes, sir. It's very
Vector
confusing,
space.
sir.
It is very confusing, sir, because, sir, in one of the previous session, it was also discussed that the 0 vector is not necessarily should be a 0, 0 vector. Because that depends on how the vector space is described. So, sir, if
how the operations is defined. Only dependent operations.
Yes, sir. So, sir, in understanding that, it is really creating a bit of confusion. So, sir, before the quiz, if possible, could you please take a few sessions specially
So
dedicated
you
to
just watch Shubham sir's 1 week before vector space videos. There Shubham says clearly. You clearly explain everything in a very, very systematic and detailed manner. Go to that
Yes,
video.
YouTube. Yeah, you can go there. Yeah.
you can watch. You can also watch NPTEL videos.
Actually,
it's not NPTEL, not NPTEL. Shubham sir's own video is there. Just 2 weeks, 7 days back, vector space video that explain everything. Explain everything.
Can you put the link of that?
Where is it actually?
Can you ping the link?
Yeah. Please put the link in chat. Who wants to be reach there can.
Yes, please put the link in the chat, please.
So it is in the it is in the
Calendar,
dashboard.
yeah.
It is in the dashboard. I will ping
So was it a solve with a session or activity session?
So this is
open session, activity sessions.
Do you remember the date of that session?
Yeah, that I forget. I am very bad at
You can check in the calendar. You can check in the
Yeah,
calendar.
week 1 content actually. Week 1 content.
Okay, week 1 content.
Yes.
Sir, this
It is very much explained. Yeah, very much.
Sir, this is all not a vector space. Is there an example where it is a vector space with no 0?
Week 1 content or week 3?
Why week 1? It will be week 3, no?
Week 3 content. Live. So go to the supplementary contents on the Mac 2, and there is a live sessions YouTube links is there.
Week 3 is about linear dependence.
access that from
Vector space and linear dependence.
No. In week 3 we study vector space, I think.
Week 3 we study vector space.
Vector space or linear dependence.
And linear combination stuff.
So I am just pasting this thing. So I'm not very habituated with YouTube, Zoom.
It is there. All the sessions are in an Excel file.
Yes, it is all the sessions. So I just paste it here.
It was the first
So,
session.
yeah, so it is the first session, and you will get every kind of questions answer here. Whatever questions answer.
Oh, thank you.
Then in this case, all these things are not a vector space. So that is the
yes.
Yeah, actually, I'm looking at operation which have 0, 0 as not a 0 element. So I am actually looking for that. So let me define.
I think that it is there.
You can take any affine flat. Yeah.
Custom operation in the affine flat.
Okay, so you are saying as a fine flat.
Yes, you can take say x comma y comma 5 as the set, and the operation can be defined as sum of the x and y coordinates usual, and 5 remains 5.
Okay, yeah, actually, yeah, that's the a fine flat will give better. Is that subspace or not? Okay, as usually we can do. Let me define an operation.
Okay, sir.
In R2, which will be different. R2, an operation. Just 1 minute. Just please give me. Actually, there are some vector spaces itself here in the.
Sir, one small question. Sir.
Yeah, sure. You can ask.
Yes, sir. Actually, before quiz 1, we will have only one revision session, sir. Because in the calendar, it is showing only one session on Monday, coming Monday.
Okay.
So, sir, only one revision session, or there would be like 2?
Yeah, as in calendar, so there will be one session. So, if as in according to calendar, you can say that. Okay. So, okay, this time I am not able to find the exact.
The graded assignment 3. No, that is also.
In graded assignment, okay.
In 3 question, yeah.
There is a question which.
Question number 1. There is a vector space. Maybe without 0, 0, 0. V4 is a vector space, right?
V4 is a vector space. Let me check once.
So what are you looking for?
An example where the origin is not the 0, 0.
No, actually here origin itself has also.
Probably in activity 3.2 or 3.3. 3.3. Go to activity 3.3. And last question, I think. Okay, no, 3.2. Okay, 3.2, 3.2, 3.2. Last question. Yeah, this one is.
As a affine flat is,
Yeah.
Actually,
so,
affine flat will give you a better Actually, affine flat is will tell you that what's happening. In R3, these things will be in R3 when we go to in R3. Yeah.
So you can construct one in R2 as well.
Yeah, actually, in R2 also can. Yeah, projecting to be in X plane. Sorry, X line.
Yes,
sorry,
sir.
X axis.
Yes, sir.
So okay, yeah, let's do that as affine flats is there. So let's say this
just
is
one question. Would there be any specific discussion with respect to week 4 today?
Yeah, actually, this session is for week 4 open session, and actually there are questions from. See, this session is an open session, and if you have a doubt itself, what is subspace? So how I will move on independent or dependent?
I was just thinking it this way, since it's obviously we have a lot of participants here, and next week anyways there would be a refresher session for the overall 4 weeks.
Okay.
Can we cover it there, and week for people who have prepared at least for the submissions and all? Can we consider week 4 today, if that is possible?
Actually, yeah. So I'm
You should do
leaving
that.
this question, and
I agree with him,
Tomorrow
sir.
is the deadline, yeah, for
a
week
fine
4.
flat,
even
a
submitted
fine flat will give a better understanding for non-zero vector, which will be considered as a vector space, which is non-zero vector, like not only 0, 0. So you can check for those and actually exist. But yeah, this depend on the operation, how the operation.
Sir, this was covered in Solve with Us week 3.
Okay. So
this,
I'm
where
leaving
there
this.
are non-zero zeros in this vector space.
Okay. So no matter if you have such kind of like you
can,
know that, just check those. Okay, no matter. So I am leaving this question, and let's discuss week 4 content. So you can one by one you can ask your doubts.
Sir, specifically, I have a doubt in this basis. How do we form a basis when some vector space is given to us and we have to check for if it is a basis or not?
Okay. So
sir, before that, can we explain the spanning thing?
Yes,
Spanning
sir.
set.
Yes,
spanning set.
Yes, spanning set.
Yeah, it will come in that one. Basis will cover spanning also.
Yes, span is with complicated concept.
Okay. So
sir, please tell difference between span and basis also.
Okay, sure. So yeah, I am taking and will tell you, maybe I will able to reach. I will whole thing. Okay, so I will try to clarify with this discussing single one. So basis before basis there is a vector space asking for a basis. That means he is asking for basis for a vector space. So I am taking a vector space. Let's say he is as defined here, x, y, and such that x plus y, x plus 2y is equal to 0. So with the usual addition and scalar multiplication. Scalar usual addition means coordinate wise addition, and coordinate wise scalar multiplication. So this is a vector space. This will form a vector space. Now spanning, I am taking a element from this vector space. Element means a vector. I am taking a vector from this vector space V, which is 1, 2. Okay, it should follow this condition. Okay, so that means 1 and 2, which is
So
2,
2 and minus 1. Yes.
Minus 2y, 2y.
So many vectors are there. So I am taking this vector. Okay. So actually still it will be actually okay, no matter. So and I am making a set. I am saying this set is yes. So spanning will cover the linear combination also. What is linear combination? So spanning of this set, yes. What it mean that spanning of this set, yes?
All the scalar product multiples of this point.
So spanning is actually spanning is actually the set
linear combination of.
all possible linear combination of this vector. Okay, so that means linear combination. Let's say I am taking two vector from R2. Now here this is different. I am taking two vector, which is a vector space with usual addition, and two vector 1 1 and 1 3. Okay, linear combination means all possible linear combination means, or linear combination of this is writing like 1 3 b 10. Let's say I'm taking 2 1 1 plus 5 1 3. Okay, so this is a linear combination of these two vectors. This is a single. If you do the as operations is like, when you will resolve like solve this element, this will be 7, and this
I'm
is
serious spanning for this example,
10.
sir. 2 minus 1 that you're taking.
Yeah. So actually I am saying what
7,
is
17, sir.
Okay, 7 and 17, sorry, 7 and 17. So this is a vector you got. So this vector is linear combination of these two vectors. Okay, so now the question is, I am saying, so let's say I am saying B is a set, and I am writing like this: A1 plus B1 3, such that A B belongs to R. So what it mean? What it says? A B belongs to R. So hope you know that set definition. This is a comprehensive kind of definition of a set. So what it means is, let me. I want to listen from you. Say what it says. What it means.
All the linear combinations of these two vectors.
Yeah, actually, if you change, so 1 7 is one element of this B, because if you change A is as a 2 and B as a 5. So sorry, 7 7. 7 7 is an element of B. So actually, B is the collection of all possible linear combination of these two vectors.
But can we stay on with it? Because I think if we take the example of vector space itself, sir, because this is slightly confusing. To take the 2 minus 1 itself, how to find the spanning?
So now, no, actually I was saying what is a linear combination, and here I said this set is all possible linear combination. Now let's back to here. So again I am writing, this is a single vector, I am writing like this. Okay, A belongs to A. So let me erase this. Okay. I am making a set which is, again, let's say this is set A, and this is the definition of this set A. What it mean that? This says that all possible linear combination, because if you want to linear combination, this is a single vector, here is two vector, so that's why A plus B kind, but here is a single vector. So that means A only A time this vector. So this says all possible linear combination of this single vector which is in the set S. So now actually this A is actually the spanning set of this. This is called the spanning set of this.
A is the span, sir.
So what mean? What is the wording? Wording means wording meaning of spanning or span.
Span of the set, right? Or it is not the spanning set.
It means generating.
So spreading.
Sir,
spreading.
Can we say?
Actually, yeah. Okay, if you are confusing, actually spanning off there will be word. Okay, let me erase this. Span of, yes. Okay, if you are confused with the word, let's say I'm span of the city. Yes.
Sir, can we say this? A spans S.
A span S.
A spans, yes. Yeah, correct. A is the span of the spanning set, yes.
Sir, A is the spanning set of, yes, you can say.
So one small,
because there are questions
here
which says like suppose W spans S or something like that. There are questions. So is the wording like same thing? Like if I say A spans S, that is A is the spanning set of S.
No. So
but
there
S
is
defined
A
as
spans, yes.
No, but A is not span of S, no?
Spans.
So here, just one clarification here is, so if
Here
we are
is
defining span,
okay.
can I complete?
Can I say something? Sorry.
Span.
You are confused with the span A span. So actually, span of yes. This let me say the clear span of yes is this set. This is the final. This is not like spanning of yes.
Okay, sir.
This is not span of yes is this set.
So here I have it also. So which means just correct me if I've got it like. So we have here the spanning set or whatever it is, span is. So 2 1 anyway 2 minus 1 is in a vector space. So all linear combinations of 2 minus 1 which satisfy the operation is what the set of all those linear combinations is a span. Is that right?
There is no operations required to only all the multiples of 2 minus 1 is in the set.
So you mean to say span is simply like nothing to do with this vector space at all?
No. Actually, it is the important. It is very important.
Yeah, that's what I wanted to know, sir. So here, not all, because A belongs to R. So all those linear combinations, or rather here scalar, all scalar multiples of 2 minus 1 which satisfy the operation is the span, right?
Which operations is itself defined because this is the inherent of this. Whatever operation you will do, this is from this V, right?
Already
no, sir. My question is
this is also will be a subspace, sir. Right?
See, already 2
No,
minus 1 already satisfy operation.
Therefore, yeah, that I got.
Therefore, operation
let one speak. It's getting completely cluttered.
Let me complete now. What I was saying.
Okay. Let me complete this. Okay, so one by one you will ask.
So, so what I was saying.
So now this set, I hope you know that what is span. Span of S is saying to be like this. Now what are the properties of span of S? Okay.
The span is not clear, so that's why I was saying, sir, actually here when you say
actually, okay, what's the doubt here again? Again, I said this set actually as here this set.
Sir, one session, sir. One session. If you could draw a line, it will be betterly represented. I think that line that represent the span of S, that 2 1 line.
That is the one thing. That is the geometrical interpretation of this span. Okay, one thing. But what is the algebraic mean? That one thing
I think it can be clarified here, sir. Just 1 minute, sir.
I think let him finish.
No, I was.
So he have doubt with this same word span. Okay, you can continue. Let me know what is your doubt is still here.
Yes, sir. My doubt was we have defined a set 2 minus 1, which is a vector belonging to the vector space, right? Okay. Now I'm coming to the next step, which is span. So span we have defined as A times, that is A the multiple of 2 minus 1, where A belongs to R. So span, which means that span is a set of all scalar multiples or linear combinations. You can say linear combination of 2 minus 1 or any vector which actually satisfies the operation of the vector space, right?
Yeah, correct.
Okay, thank you.
Excuse me, sir. Sir, can we write A 2 minus 1 as A into 1 0 plus B into 0 1?
You are writing 2 minus 1 as
A bracket 1 0 plus B 0 1.
So what is A here, B here?
A, sir, A will be 2 and B will be minus 1.
1 0 plus, okay, B will be minus 0.
No.
Okay. So
Sir,
actually,
hello.
Yeah.
So extending this thought, if our set S is say 1 0 0 plus 0 1 0 plus 0 0 1, then the span of S will be everything in R3.
So no, that is a very different thing. As here, this is only 2 coordinates. So how you are saying about the 3 coordinates, which is 0, 0, 1 kind of one. Here is only 2 coordinates.
I'm sorry, I could not hear you, sir.
My voice is clear right now.
Yes, sir. Yes.
Is it clear? My voice is, there is noise from background, something? No?
Yeah, there is some little noise, sir.
Okay. Now, I hope now it's clear. Okay. Yeah.
Yeah,
Now
it's better clear, but it's not.
Okay, let me check once more. Now is it clear? Is it?
Yes.
Yes, sir.
Better.
Yeah. Okay, so no, it's clear.
So, as just now you told, there is no 3 kind of coordinate lighting 1, 0, 0. There is only 2 coordinates. So we will only deal with the 2 coordinate, like here writing like coordinate wise like this. Okay. So this is a different thing. I will back to here. This is a different thing as you are writing. I will back here.
Okay, sir.
This is a very different.
Sir,
Okay, sir.
if you take one more vector in
That's why
S.
Okay. So I will take. Okay, I will take. You just keep your question. I will back to here. Okay. Let me finish this one because waiting this one up. What will be after this? Okay. So now you know that what is span? Span I just wrote in this form. Now the next question is, what is the use of this span? Why we want this span? So actually, if you check here, I am taking a vector. I am taking a different vector which follow this condition. So tell me an element different from this to 1. What will be? Minus will be okay.
Voice is not clear actually.
Shubham, you may like to check the audio connection. Some jarring noise is coming around.
Okay, just 1 minute. Just 1 minute. Hope it's better now.
Yes, sir.
Yeah, this is better.
Okay. So yeah, okay. Now I am taking a vector different from this 2, minus 1. So is it this is vector final, right? This follow this condition. Okay. So now what is I am saying? What is the relation here with this span and with this v? Why we want this? Okay. So I am taking a different vector which is 4, minus 2. So if you see that here, I am writing
So your voice is not clear.
4, minus 2
Completely cracking, sir, your voice.
Yes, sir, voice is lagging.
Minus 1. Totally. Just 1 minute. Let me check once. Is it clear now? No?
Yeah, this is better. But earlier it was cracking.
Okay. So I hope now it's clear. Okay. Okay. Is it clear, right?
Yes. Now.
Yes, it is.
Okay. So this 4, different vector, which is I am taking a different vector 4, minus 2, which you can write as 2, minus 1. Okay. You can write, right? Because the addition, operations define like usual addition and scalar multiplication. So you can write like this. So now back to here. See that what's happening. Is this element from this set or not? This is span.
Yes, sir.
Yes, right? Because A is working as here 2. Yes. Now I am taking a different element. Let's say you can tell what a different element with different from these 2. You can tell a different element. Am I audible?
Sir, 6 and minus 3.
6 and minus 3. Okay, I am taking 6 and minus 3. So this is a vector from this V vector space V, and now I am writing this vector as 3 into 2 comma minus 1. Is that set is this vector is from this set or not? Yes, right?
Yes.
Yes, sir.
Yes.
So what's happening here with the span word? Actually, each element of this set, each element, or you can say each vector from this vector space V is actually the same this span, right? This is also a set with different notation. This is also a set with different notation, right? What's happening? If you check, this will always true. If you take any vector from this V, and you will modify something and you will say that, oh, this is the element of this span. Yes. So what's happening? What's here is going on? Span.
All the vectors in the vector space are same as in the sets of the span. Are you saying that?
So all vector of this vector space is nothing but this element of this span. Yes. Okay. So that's the important here span.
Sir,
Span is actually, so now.
So can we say that, sir, 2 comma minus 1 spans the whole R3?
Yeah, so now the next word is 2 comma minus 1 is main leading here, like main in lead, like here is in main lead 2 comma minus 1. That means 2 comma minus this single vector span whole this V. That's the here happening span. Linear combination of this single vector is the element of this V. That's the here meaning is span. So that now you can say span of S is the vector space. Span of S, like here what's happening. Span of S is the vector space V. Now the other word is actually span of this vector is, you can say, vector space. Span of this vector, span of this set, 2 comma minus 1, is the whole vector space. So operation you are taking as in V, okay? Because you are taking this this vector is from V, so you will do the operation as in V is, as is the operation is defined, usual addition and scale element. Different operation, if there is different operation is given, you can go with that.
All the vectors in the vector space will be multiples of 2 comma minus 1 here.
2 comma minus 1.
Oh.
So 2 comma minus 1, this vector span, yes. Sorry,
sir,
this vector.
That means it will be a line, sir.
That means it will be a line. Now that is the line is like coming to be in geometric kind of, right? So I am saying here only the algebraic meaning. That's
sir,
the different line.
Geometrically, that means it will be a line, no, sir?
Yeah, actually this V is actually in R2 as a line it's happening. So that is
how it
apart
has
from
been
this.
converted in R3, and when we add the vector
I will back to geometrically. I will back to geometric. Let's finish this one. Okay. So final thing is this span, this vector. So if you have doubt now regarding this, I am saying span
sir, so we can change this leading vector, right? 2 comma minus 1.
Okay, you can say this is the leading vector. Okay.
So in that case, geometrically, then there will be infinitely many points actually in the space. The span will be infinite, is it?
Geometrically, let's keep geometrically as a different thing. Okay.
Okay. Otherwise, okay. So any scalar multiple. So 2 minus 1. So any point on this line will be a part of the span, right? So there will be, the span is infinite. Is that so?
So actually this set is infinite set, right? What is the cardinality of this set?
Infinite. Because
infinite, because R is multiplied here. R is infinite. Like here is, you change the A and you can get infinitely vectors are there. Okay. So now the word is came for basis.
So, sir, can I ask one question?
Okay.
Sir, so here the leading vector is 2 comma minus 1. So that also we can change, right?
That we can also
change.
Change.
Yes.
You can change. You can take now 6, 3.
Yes, yes.
And I am taking this different set S prime, which is 6 comma minus 3, a different vector from B. You can check this vector is from B. Okay. Now
Yes.
span of S prime is nothing but writing like as A time 6 comma minus 3, such that A belongs to, or you can make different also. So A belongs to R. So this is the span of this S prime.
Okay.
Still you can check that this vector itself too, like here is happening,
Yes.
6 comma minus 3 also can span the whole vector space V.
Yes, yes, yes.
So we can also say that it spans the entire XY plane.
No, actually this is the different thing. Now span, this is not spanning whole R2, whole R2.
So but in lecture, sir said if span is equals to V, here this span S is equals to V, the vector space. So we can say if the vector space is in R2, right?
So like here, this V is not R2, right? So how you will say this is equal to R2? This V is only this condition.
Subset of R2.
It is a subset of R2.
Yeah, this is a subset of R2, but it is working as a individually as a vector space with the as I operation is defined. Okay.
Okay, so it won't be R2. S won't be R2. Okay.
Okay. Now the wording came for basis. As you know, okay, this set span of this set is whole vector space. Now this set contains single vector, and just you can remember that, or you can say single vector, or I will tell you why. Single vector is always a linearly independent vector. Why? The reason is why, just take the linear combination equal to 0. This is 0 implies A equal to 0. So single vector is always linearly independent. So now what is the definition of basis?
So sir, if it is a single vector is a 0, 0 vector, then also it is a linearly independent?
No, 0, 0 is 0. If 0 vector is there, 0 vector is always dependent vector.
No, if only
because
0, 0
if you
is
check like the
single non-zero vector is an independent vector.
Okay.
Single non-zero vector is independent vector.
But if it is only 0, 0, then it is a dependent vector.
Then it is a dependent. The reason is also, you can see that here I am writing B time linear combination of 0, 0 equal to 0. So what it means that 0 means here 0, 0. Okay. 0, 0 means here 0, 0. Means if you take 2, 0, 0, still it gives 0, 0. So you got B as a non-zero. So that means you will say, okay, this is dependent. That's why non-zero is a linear combination. We are getting non-zero. So that's the reason 0 Z is always dependent. Or zero vector, not 0, 0. Zero vector in a vector space is always linearly dependent. That's the word. Okay.
Sir.
So,
Sir, how can we define, sir, that let's suppose, sir, I have x comma y as a y vector space, sir, and the condition is x and y both belongs to R. Operation is. Then, sir, how much points I need to span the whole R square?
Whole R2, okay.
Yes.
Whole R2, na? Yeah, so okay. That's the I will back. I will take different R2 itself, the vector space. I will tell you. So let me finish this one. I continue with this. So let me finish this. So now the word come basis. What, anyone can unmute yourself and tell what is the definition of basis?
Basis is an independent set in that vector space, which will span the whole vector.
Those who are maximal independent and minimal spanning.
So there
Minimal
are
spanning
many
set.
more definition. It's used. So I'm writing basis and 3 definitions also. The first definition is collection of I think let's say yes is set to be basis of a vector space V, when it span
The whole V.
And collection of yes is the
Linearly
collection of linearly
independent
vector.
factors.
So is yes this span this yes here our the main yes follows this or not? Follows,
Yes, it
right?
follows.
Span
Yes, yes.
and independent also. So yes is actually a basis of the. Now you can say.
Sir,
I am
if you
writing different. Okay, continue. You can continue.
Sir, what is maximal independent and minimal?
So I am writing the different definition
Yeah,
also.
sir, it is difficult to understand these concepts.
Maximal linearly independent set in a vector space is a basis of that vector space. The second set is the third definition is there is a minimal word is using. So can you tell me what is use the in basis set? What is the definition for using minimal word?
Minimal spanning set.
If it means that if we delete any of the vector, then it will not span the whole V.
So minimal spanning set is a basis of that vector space. And is there any, if you have any other definition, any other, if what's coming like saying to be basis, sir have said any? No?
Can it be a minimal linearly dependent set?
How it can be?
Cannot be.
No, minimal dependent is not in basis.
So there are three definitions. Each I will discuss one by one. So one we have seen just now what is happening. Now maximal linearly independent and minimal spanning set. Okay, we will see these two. So now I am back to R2. Just now I said I will back to in R2. So R2 is a vector space with usual addition and scalar multiplication. Okay, with usual addition and scalar multiplication. So please give me a two vector. Please give me any two vector, or give a vector. I will take another vector.
Sir, 1,
anyone. 1, 1. Okay. Or if you want, okay, I'm taking a second vector as 2, 3. Okay, I'm another taking vector 2, 2, or maybe okay 2, 2 I'm taking. So these three vector I am taking. Okay, let's say this is yes, and I made a set. Hope you know R2 what is a vector space.
It will
R2.
span, but it is not the basis.
So we will see that it. Okay. So I made a set using these three vector. Okay. Now let's check linearly in these three vectors are linearly independent or dependent. So what is the process to check? This is dependent. So what is the process to check? A comma like writing it a linear combination of these three vectors.
In this case, it's simple, sir.
We can also analyze from the dimension of R. If it is greater than dimension of R square or 2, then it is linearly dependent.
So that is a different thing. So you know the dimension word, that's why you are saying, but who don't know how check the set is like my question is this set yes is a basis of R2 or not?
No, sir.
No.
So you know the reason dimension kind of word and you can directly tell, but what is the process to check? What is the process to check? So checking that, first check is this set is linearly independent or not.
Yes.
So how to check linearly independent? write the linear combination and make it equal to 0. Okay. Now try to find the values of A, B, and C. So it will be A, comma 2B plus 2C equal to 0. And the second is A plus 3B plus 2C equal to 0. Now this is a system of linear equation, and you know how to find the solution. There are so many ways: Gauss elimination, grammar, there are finding the inverse. So Gauss elimination is the best process to know, not the best, like very easy process to know the solution of a system of linear equation. So finally, when you solve this, I am leaving to you. When you solve this, you will know that A, B, and C may not be 0 exactly. There are some values which make this can be 0. Not exactly will be 0. There are, because the reason is there is infinitely many solutions. Hope you know that how it's happening.
Yes, sir.
So that means this set is not linearly independent. Okay. So this set is not linearly independent. So that means one thing we checked. Okay, one thing we checked, this set is not linearly independent. Okay, no matter. Now let's check for span. What will be the span of this set? Now you can tell me.
R2.
What is the span? R2.
R2.
Why?
Because the linear combination of the three vectors will go R2.
So 1, 1 and another 2, 3 is a linearly independent. Two linear independent vectors is there.
Because sir, V is equals to
And
R2.
yeah, R2 correct. R2 is correct.
Okay, so let's check that. Let's write the span. So what is the process to write the span? Is same as writing A. This is the span, right? This is A B time 2, 3 and C time 2, 2, where A, B, and C belongs to. This is the span.
Yes, sir.
Okay. Now this is the span of yours. Now take any vector from R2, because we are doing vector space under these things we did for under vector space R2. So take any vector. You can tell vector any vector, and we will try to find. You can tell me. Let's find. Let's take a vector from R2.
5, 5.
10, 10, 15. I'm taking. Okay, no matter. So 10, 15. So 10, 15 can be written as. Actually, you have to find the values here. 10, 15, like writing the solution of this solution system. So,
or sir, we can do sir it right, making three equation or sir equation.
So actually the reason is actually when you see that this 10, 15 can be written as some value will be alpha time 1, 1 plus beta time 2, 3 plus gamma time 2, 2. Actually, this can be written. If you check that, how to check? Just solve this system of linear equation, right? You will get the value of A, B, and C. So that means any vector of R2 can be written as the linear combination of these three vectors. What it means that again the span of S is whole vector space R2. Now the next word is coming. Is this vector is linearly independent for basis? So we know that no, S is not a linearly independent set. Just now we checked here. So that means S is not a basis here. Yes. Now let's we check with the first definition just now. Now again I am writing S as 1, 1, 2, 3 and 2, 3. Now I am taking the second definition. Maximal linearly independent set in a vector space is basis of that vector space. So actually this says that this not says the process. This says that try to find the vectors which are linearly independent in R2. This the second definition says The second definition says try to find the linearly independent vectors in R2. So how we will find? The process is take any vector. Any vector, single vector is linearly independent.
Yes.
So let's say 2, 3 I am taking, or let's say 1 by 2 and 1 I am taking a vector. This vector is linearly independent. Now I try to find another which is linearly independent to itself. So how we will find? So to find that, okay, linearly independent we want. So try to guess that, or maybe try to find. Let's say I'm writing 2, maybe 1,5. Is this 2 vectors are linearly independent?
Yes. Sir, instead we can use Gaussian elimination.
This is try to guessing that. Actually here is you have to try to guess that I take a vector, I have to find another vector which is linearly independent. So more time, like this is 1 by 2 you take. So take a vector and check that these 2 vectors are linearly independent. So 1 by 1 each time if you do, you will reach that. That is a big thing. But if you take a random vector and check that this is a linearly independent or not. So actually if you see that these 2 vectors are linearly independent. Now try to find the next linearly independent. Okay, let's try to find. So if you try to find the next linearly independent, which is independent these two vector.
Sir, then it is a kind of trial and error approach.
Trial and error approach. So that's why this method is the best thing. Is finding the span. The first one is the best thing to find the basis. Try to find the span of that and then move on to the check the linearly independent. So if you try to find here, you will never get a linearly independent. Always you will find a linear combination of these two in R2 case.
Yes.
So that's the mean is maximum linearly independent. Means we reach the maximum linearly independent. There are only 2. There is no third one. So that's the meaning of maximal linearly independent vectors in that set.
Yes.
Now next is minimal spanning set. Minimal spanning set. So we back to our same yes. Okay. Now we span here, wrote the span here. Okay, this one. This is the span of yes. Now remove a vector from this set. Please everyone mute yourself. There is some background noises coming. Okay, thank you. So just let's remove this one. I am removing this vector from this set yes. So let's say this is S prime and I removed. Okay. Now try to find the span of S prime.
But it is not R2.
So we will reach a very we will reach in trouble. See, let's see that I am writing a linear combination which is this one plus this one, where A comma B belongs to R. Okay. So this is span of S prime. Okay. Now take a vector. Now we need to check that is this span is exactly R2 as our V is R2. So let's check that I am taking itself this one because 2, 3 I removed here, which is element of R2. So let's take 2, 3 from R2 itself. This 2, 3 can be written as linear combination of this one.
No, cannot.
So what is the process to know? So let's do that. How 2, 3 is not the linear combination of these two. So let's say I am writing A comma 1. I suppose here the process is to check that 2, 3 is linear combination of this one or not. So suppose this is true, the linear combination of these two. Okay. So let's solve this system of linear equation. We will reach a system of linear equation which is A comma 2B, which is 2 here. If you compare, or let me write the proper way, which is A plus 2b first coordinate, and second coordinate is a time again 2b, which is 2 comma 3. Let's compare here. So we got a comma 2b is equal to 2, and a plus 2b, and a plus 2b again the second coordinate is equal to 3. So what we reach here? We
No
reach
solution.
Contradiction.
No solution. So that means this 2 comma 3 is not a linear, is not the element of this span. What it mean that this span, this S prime is not spanning whole R2. So still that means what? Let's come to our third definition. Minimal spanning set in a basis of that vector space. So we took here S prime, and actually this is not spanning this R2. But as we here S prime, when we was here yes, and when we span here we get the span of S. Okay, it spans. Okay. Okay, I okay. Just I
So,
made
sir, for
a jump
R2, we
here.
will always need three vectors, right? For
two vectors.
Two vectors. So let me. I made a jump here. Let me say. I made a jump. That's why maybe it may confuse you. So I am explaining you. Okay. First thing I did. Yes, I took a set. Okay. And I know that. Okay, I got that span of yes, span of R2. So I checked that is that linearly independent. So we got that no, this set is yes is not linearly independent, and actually this set is span whole R2, but what we missing? One thing we missed here, not missed here. Only I want to tell you. So okay. Till here we know that span of yes, span whole R2, which is exactly R2. But when we took a subset of yes prime, subset yes prime, we got that this is span of this yes prime not equal to R2. Okay. Now take another subset of yes. Let's say double prime, which is 1 1 and 2 comma 3. I just remove from this set. I am removing first. I remove this one. I got that set is not which we obtained S prime is not spanning. So now let's remove this L vector from this S. Okay. So this is the set here S prime. Now let's take the linear combination, which is span of S double prime, which is written as a comma 1 1 plus b 2 comma 3 a comma b belongs to. Okay. So that means now take a vector. This is the span. Now take a vector from R2. Let's say I am saying alpha beta from R2. General vector I am taking any vector. Alpha beta can be any. Alpha is any real number. Beta is any. Okay. Now is this vector can be written as in this form? Is this vector is element of this set or not? Let's
Yes,
check
sir.
that. So let's check. This is 1 comma
Yes,
1.
yes.
So suppose this is happening, which is alpha beta. Now if you solve this, it will be a plus 2b is equal to alpha, and a plus 3b is equal to beta. Now this is after getting this, solving this equation, we reach a system of linear equation which can be solved using the Gaussian animation or directly here. This is writing like this, and this is minus b is equal to alpha minus b, and b equal to beta minus alpha, and now you can get the value alpha a also. That means beta minus alpha, some a value will be a here. A you can get alpha minus 2 times beta minus alpha. As you know, I am just I'm quickly doing it, and this will be 3 alpha minus 2 beta. So a here will be 3 alpha minus to beta. You can check if I made wrong. You can check yourself, because you have to find the alpha beta value. That means this vector can be written as 3 alpha minus 2 beta 1 1 plus beta minus alpha 2 3. Means this alpha beta can be written as linear combination of these two vector. If you alpha beta, if you are problem with alpha beta, let's take a particular vector which is, let's say, 5 comma 2 here. So your a will be here 15 minus 4 time 1 comma 1 plus b here is 5, b is 2, and alpha is 2 comma 3. And I'm like you are able to find this vector is actually this 5 comma 2 is belongs to this span, and this is a like a particular vector. You can check for each, and finally you will reach that this span of S prime is a whole R. So actually when you reduce this S to S double prime, you know that okay, we got a span of
Sir, for checking, we just need to take a general vector from R2 and then solve the equation, right?
and solve the equation, and you are able to solve that.
And if it is solvable, then we
Then
have.
you will say, yeah, okay, there is a
Sir, the general vector we take to check the condition, will that be satisfiable for all the vectors?
Condition means here this is a condition to check, so that means you have to checking this one.
Yes, sir. Taking one single case of the general vector, will that be able to satisfy all the conditions for?
No, that will be not enough, because maybe you randomly reach at that point where it can be written as linear combination, but there can be possibility.
Yes, sir. So in that case, like how should we
you have to check at least 3 to 4 vectors.
Even
so you have
even
to
if we take
at
3
least
to 4
randomly
vectors
2-3
and those
vectors and check.
Sir, even if we take 3 to 4 vectors and those satisfy, will there be any random?
So if your way is correct, okay, no matter. If you are in like this is the kind of bad luck, you chase randomly and you are reaching those and you click that option.
After
but
doing
yeah,
for
that's
general,
So
but the
trial,
process
we
is,
can check the options for trial error in those cases, right?
you can trial error. Otherwise, take a general vector and do the best thing. But it
But
will
whenever we are faced subjective question, not like an MCQ question, like we have to check if you are checking for.
Then you have to go with the general vector, like writing alpha beta and do the process of.
Just conceptual understanding. If I start with linear independent, that is a null set, I start with, and from there on I keep on adding a vector till such time I reach a span, that is an algorithmic approach.
That's the algorithm. Actually.
But if I start the spanning side and I keep on reducing it to reach to a linearly independent set, how do I do it in an algorithmic way? Because just like the way it happened, if had there been some 15 vectors, which is in a span set.
Actually, what I am saying, I just try to tell you what is the meaning of minimal. Otherwise, the process is first you have to. What is the process is first to take you have a zero vector. First, you have to assume S is 0, and is that span of this S is spanning whole R2 or not? If not, then you have to take a vector and add in that. 0 means 0 0 here. So you have to take like not 0
which
0,
doesn't
0
exist in this span.
Which doesn't exist in this span. So take another vector, like 0 0 is only span 0. So take a non-zero. Sir have said in video, if you see that non-zero vector, take any non-zero vector and first do that its span. Let's say this is yes, and is its span R2 or not? If not, then take another non-zero vector which is different from this one. You have to take another, let's say 1, 2, and check that span of this one is span whole R.
I have a doubt in the solution you brought in the previous example. Sir, do we want A and B in the form of alpha and beta only? Like we cannot have. So yeah, please scroll up.
Okay.
Yeah, you found that B is equal to beta minus alpha, and A is equal to alpha minus 2 B. So we have to have A in the form of alpha, beta, and
you have to. That's the meaning. That's the meaning says that. That's the meaning says you are reaching to the finding the value of A and B in the form of alpha, beta, which is alpha, beta means you have alpha have a particular value, beta have a particular value. So you are able to evaluate the expression.
So let's say that we have three vectors, and R a vector in R3. So it's we would have A, B, and C. Right.
So that is that's will take long process to solve.
Then that basis should have at least three. It should have at least and at most three vectors only. It cannot have more than that or less than that.
So that's the word I came for dimension. Yeah, correct. That's the word for telling to be the dimension 1, 2, and 3.
And there were some questions. So I don't remember exactly which one, but there were some activity questions which when I was solving, I found a similar problem wherein I could not get A and B in terms of alpha and beta. So that means that that particular set is not the span, not the basis of that.
So if you are not able to get, like here it's happening, like here is happening, like here, please everyone first mute yourself first, please, otherwise I
Please mute.
I muted to all. So so there, if there is such possibilities happening, that means like maybe there is a like L3 alpha minus 2 beta plus 1, or maybe some constant is happening. That's fine. If apart from this is happening, then you are in a trouble. That means you can say no span, it cannot span. Okay. So I hope I told you the meaning of each. Where is that spanning? What is the minimal spanning? Where is that? Okay. So I hope you understood what is the maximal mean and minimal spanning mean, or span, or a basis also. Is it clear to all of you?
Yes, sir.
Sir.
Yes, sir. But I have a question. Like, if we keep increasing the elements of the spanning set, likewise, we will eventually end up getting the standard basis.
Oh, no, not a standard basis, a basis. A standard basis, a different word. Basis, you will reach a basis.
Sir, I mean, if we, we know what is the standard basis. So accordingly, if we increase the thing and get that, will it be wrong?
No, so actually, let me tell you. So like somebody says that he is a vector space and it have dimension 5. Okay, it have dimension 5. You don't know, but you said but only he told you that find a basis or find the span, or let's say spanning set, or you can say a set yes which span whole V. Try to find a set yes which whole span V. So and he told you that it have dimension 5. Okay, so you start with the non-zero vector, like checking whatever a non-zero vector A. Okay, and keep adding B, C, D, like adding. But when you reach 5 and when you reach 6, if you reach 5 itself, and if you try to find so if you write till E, you will get that span of this set will be span of this set will be whole V. So you will not need to go in the next F. One by one, if you will check correctly, that means a proper way. So only till reaching E, you will find that, oh, it is span whole V. So that's the meaning of minimal spanning.
Sir. Sir.
Yeah.
Sir, my vector space is sir R5. So then how many elements I needed to span it whole R5?
So that means you need, that's I mean said 5. Here are 5 vectors. So 5 vector at least needed to span whole P.
And sir, my doubt is in sir dimension and rank, sir. I am not specified the dimension and rank.
So let me tell you, sir have told you dimension and rank for the vector space. That means it is the same. Otherwise, when you come in matrix, the rank of a matrix is different word, and dimension of a vector space is different thing.
But sir, in this course both the same, na?
So for example, sir, my matrix is 1 by 2.
No, you
sir.
didn't get. Okay, let me. But let me say. I'm saying. Here I'm. Sorry. So.
Your voice is breaking, sir.
So what I want to say. Let's say. Is it clear now?
Yes, sir.
No. Let me check once. I hope now it is clear. Okay.
Yes, sir. It's clear now.
So the question, it will be like this: a rank or dimension of a vector space. If somebody is asking, so you will take this rank and dimension of a vector space. If this is one question, this is another question. Rank of the matrix A. These two words are different. So when the case is rank and dimension of a vector space, then these two are same. Okay.
Yes, sir.
And usually the word uses to be dimension, not rank. Okay. No, not rank means most of the time it can be, sir, as sir have used. So most of the time the word uses as a dimension. Very less time you will see the rank. So don't worry with the word here for the dimension of a vector space. Please concern the rank word with the matrix. Okay.
Okay.
So be clear. Most of the time, if you see in the itself activity, graded, practice, quiz, or anywhere, you will see the most of the time or always the word uses dimension, not rank, for a vector space.
Sir,
but the word.
So for vector space, can you please explain how we should find dimensions if
okay, I will
some
back to
constraints are there? Yeah.
Okay, I will back.
Also,
So
also
please
for
make the
matrix.
differences.
Also
Please
for
note
matrix.
these two differences. I am making here differences. Okay. So but this rank word with the matrix always, most of the time you will see. So please note with that. The case with the vector space, these two are same, but most of the time you will see only the dimension word, or most of them always in this quizzes in the sense activity, graded, practice, you will see only the word dimension. You will never see the rank of the vector space. So dimension word you will say. Rank of the matrix you will see. Rank of the matrix. Okay. So be clear with that. Now let me back to the dimension word. I'm always choosing the dimension word. Okay. Now I will not take the rank word. Rank word, whenever I will take the rank word, it will come to the matrix. Okay. So what is the dimension of a vector space?
Sir, I have a very basic question. Question is that if I have an equation and that is not a vector space, can I find the basis of that space?
No.
So suppose I give you
actually when the word came for dimension or basis.
So suppose I have an equation 2x plus 3y equal to 1. Can I find the basis of this space? If somebody asks me this question.
So I am let me tell you, your answer will be in the what I am saying. Whenever somebody is asked dimension of a vector space, that means that vector word should be added. Like if you are saying these things, so it will be a proper ways like this. Okay. This one. This is the set. Okay, let me erase it. This is the set. Let's say this is B, and he will give you operation also. Okay, he will say find the dimension of the Now find the dimension, not dimension. First he will say this V is a vector space or not. So word came for dimension. Whenever there that set is a vector space, then we will say then we will talk about the dimension. If that set is not form the vector space, then you will never talk about the dimension. Okay.
Okay.
So here is the case that this set does not form the diamond. Will not form vector space
Vector
with
space.
usual addition and scalar multiplication. Let me give the operation.
But sir, my question is that suppose I write a set that is the span S equal to A into 1 minus 1 for this particular set.
Span of 1 comma minus 1. Okay.
Okay. Now every point in this line will be span of this.
So let me again complete the word. Span, dimension, basis word only came after the vector space word. Okay. So whenever we talk about, you have to check first this set is vector space with the operation whatever is given or not. If this set is not forming the vector space, you will never go the word next is span, dimension or basis. Clear?
Yes, sir. Yes, sir.
Okay. So as here you have to check this set forms this set is a vector space with the whatever the operation is not is there or not. If this form, then we next word is span. So here is your, I am saying your question is wrong, because the word here this will not form a vector space with whatever the operation I have given, that usual addition and scalar multiplication. Okay. So your word will came span, dimension or whatever the basis word after the vector space word. Okay. So now let me finish the thing dimension. So I am back. I am coming back to my previous year about this one. When we know that yes, this set
And
yes,
after
this
clearing
previous one
this
this yes.
concept, sir, please take some questions of 4.3 activity, sir.
Yeah, I will surely take. Okay. So the dimension is nothing but a single word, number of element in a basis. That's all.
Yes, sir. Actually, when there are some constraints, and there is a question like what is the dimension of this vector space, then how can we find out to figure out where independent variable and dependent variable?
So the dependent and independent variable is till week 2, right? Only till week 2.
Sir, will the answer to this question be the number of independent constraints in the equation?
Yes.
Number of, sorry.
Like if a vector space is given as x plus y plus z equals to some constant, then
No.
what?
So your word
what
is
will be the dimension?
Again, your x plus y plus z is equal to some constant, not 0. Then that will not be a vector space.
Sir, if it is 0, then what would be the
let's
dimension?
assume this is 0. Okay, so that is a vector space with usual
But
addition.
there is a question in solve with us, question number 10.
Okay.
There is my question is like that.
Okay, let me finish this. So what is the process for the dimension? I will back to your the solve with assignment. Okay, so what is the dimension of the vector space? First find the basis, whatever till now we did here. Same process you will do to find a basis and count the number of element in that basis. Just say that is the dimension of the vector space. That's all. The next step, just finding the basis. So the question is, it will be like this. Somebody says V is a vector space. Find the dimension. Okay, this is the question. So what is the process? You have to find a basis of V. Okay, then count the number. Let's say I am saying this is S is the basis. So cardinality means number of element in S is the dimension of V. That's all. That's all. Nothing else.
Yeah,
That's
but
And sir,
some
what we, sir, sir,
there
in
are
case of
some
matrix, sir,
constraints
how can
also,
we
sir.
say that the dimension is what?
sorry.
Sir, in case of matrix, sir, in activity 4.3, sir, there are some questions, sir, about, sir, matrix 1 cross 2. What is the dimension of matrix 1 cross 2? Sir, how can we solve that type of questions?
Okay, okay. So, yeah, okay. I will back to your activity first. The girl have asked about the solve with assignment. One question is there. Okay,
Week
you
4,
can
sir.
continue
Week
with that.
4.
Then I will. Okay.
Week 4, sir.
Week 4.
Yeah.
Which
Solve with us.
solve with us. Which question number?
Question number 10.
Okay, question number 10. Okay. Let V be a vector space which is defined as follow with usual addition and scalar multiplication. Which of the following set forms a basis of V? So how to check that which will form the basis of V? So first thing is the first thing what is needed, you have to check each element of this is from this set or not. How you will check? You have to take this element and put the values coordinate wise in this equation, and if it is satisfied, then you can say, oh yeah, that's the correct. So maybe there are some option which you can say that this set is the subset of this V. Okay, the first thing I mean to say, this is a set. So which of the following set is a subset of V? First check this one. Okay, the second thing is now check for linearly independent and dependent thing.
Yes, sir. Related to this, there is a question 11. Yeah. Here is find the dimension actually. Yeah. Question number 11.
Same thing, right? Or maybe different. Okay, whatever the. Okay. So dimension is, so now here you have to find the basis of this vector space. So just now I told you the process, how to find the basis. So as here, okay, that's the here your question is two constraints are given here, this one and this one. So this is a hint is given, right? You can use this one to finding the basis. You will use these constraints to find a basis of V. After finding the basis of B, am I audible?
Yes, sir.
Okay. After finding the basis of this, we just count the number.
So we should first find out the independent variables, and then actually there is a step given there. First, we should find out how many independent variables are there. So actually, I go through, but I just want to explain with if you actually explain that one.
No, here is not any feedback. Is that hint is given only here. Okay. So okay, I will discuss to find the basis of this vector space. Okay, how to find the basis of this vector space. Then we will go to the dimension word. What is the dimension? So let me take this. Hope maybe many of you will get this, how to find the basis of this vector or other vector. It will help.
There in key points there are steps, I think.
So in key points have the, in key points the steps are written.
Yes, yeah. Here.
Yeah, so in steps as you will follow. Actually, this says that if you see that here, the set, this one is the linearly independent set, and this is the maximal linearly independent set in V. So these steps tell you about how to find a basis just now as I was discussing.
So first we have to form the matrix form these equations are given, and then we have to find out how many independent variables are there, and then we can
independent vectors. Okay, continue with that. Okay.
And if there are 3 independent variables, then we can say that dimensions is 3, like that.
So yeah, actually, yeah, that's the correct. If you are able to find the 3 independent vectors, so the dimension is that. Yeah, correct.
So first we arrange the equation that is given x plus y in the matrix form, and then we reduced in row echelon form, and then we find independent variable, and then we can say that is the process, no?
Yeah, correct.
Okay.
Sir, could you please explain what she said?
So actually she is saying to be try to find, she is telling the process to find the dimension, and actually she is jumping to the directly to find the basis, dimension of that. So actually let me take this example and tell me how to find the basis of this vector space B. Then we will count the number of element in that basis and say dimension this will this. Okay, so please tell me what is V here again. Maybe I am not able to see that. What is the relation in XYZ? Here X plus Y, Z plus W. The second thing is
X plus W is Y plus Z.
X plus W, Y plus Z. This is equal to. So this is the V here, and X, Y, Z and W belongs to R, and the operation, now see that operation is okay.
Operation is given.
Okay, you
X plus Y equal to Z plus W. Two operations are given.
No, actually, okay, find the dimension of the vector space V, this one. Okay, assuming to be the subset of R4 with usual addition and scalar. Actually, now see, such kind of, if there is given, you can by default assume that operations are usual addition and scalar multiplication. Like if someone is not mentioning the operation, that means coordinate wise addition and coordinate wise scalar multiplication you can do. So that means you can say this is forms a vector space with usual addition and scalar multiplication, and we will try to find the basis of this vector space. So these are the condition. These two condition will help you to find the basis. So next, to find various, let's see, this one is you can write it as x plus y minus z minus w is equal to 0, and this can be written as x minus y minus z plus w is equal to 0. Okay, and this, you know that this is a system of linear equation in 4 variable x plus y, x, y, z and w. So now this is the process to find. Otherwise, the thing is, now you have to find a vector in this set following, and again a spanning kind of you have to check. But this is a simpler way which I am going to write here. So this is a system of linear equation, and try to find the solution of this system. What will be the system solution of this system of linear equation? Just write the Gauss elimination. 1 1 minus 1 minus 1, and this is 1 minus 1 minus 1 1. Okay, and reduce it to reduce row echelon form, or row echelon form is also enough to find. So this is 1 1 minus 1 minus 1, and if you subtract to be directly here, you will get 0 here, and this is minus 2, And
Sir,
this is
the values of
0 here, and
this
this will be
elements
here,
of the row,
and
we
this
have
can be
taken
written
that
as 1 more.
arbitrarily.
The
No, no, no. Here the values
coefficient
are
of.
coefficient, right? Hope you know that
Okay,
how
okay,
to
okay.
find.
Yeah, got it, got it.
Okay. So then after, just make it in reduce row. Sorry, row echelon form is enough. Divide by with the -2. It will be 1 here. It will be 0. Oh, 0 is here. This will be -1. Okay. Now this is in row echelon form.
Yes.
So now what is the solution of this system of linear equation is writing to be back to with our
equal to
x, y,
W.
z,
One is
w back to with our back to our system of, like, after getting the reduced row, you can back to a system of linear equation which is written as x plus y minus z minus w is equal to 0.
It's
And
still
the
not
second
reduced
one
row,
is
right?
no, it
It's
is not
added.
reduced row, it is row echelon form.
Okay. But if you do a reduced row, then we can find about the independent variable and dependent variable.
You can find the independent and dependent.
That is the question.
That's the question. Means no, actually this question is for finding the dimension. So actually I'm
Yeah,
first
the
what I'm trying to find
number of dependent variable will give the dimension.
Number of independent variable give the dimension.
Right.
But this question I am trying to find the basis of this vector space. Okay.
For
Otherwise I
finding
can
the basis,
directly jump also.
for
A
finding
basis of this.
no,
Finding
no.
a basis.
Yeah, understood. So I'm just referring to the lecture, and correct me if I'm wrong. It says that, before I do a row operation, this vector should be put in as a column vector, and on that I have to do a row reduction form. Is that correct? Or I can put it as a row vector itself, and on that I do a row reduction.
That for the pivot part.
Yeah, so
Actually,
Pivot part.
there are so many ways to find the basis and to find the dimension. Okay, there are so many ways. Actually, while looking to, like, if you are very with like you did so many example, you are very much practiced, then you can while looking you can say, oh, dimension is 2 or dimension is 1. While looking you can say, but I'm telling, maybe many of you I am taking this example, and it will help to find the basis of different vector space. You can do the same process also.
Correct.
So let me finish this. So this will be, I am back to the system of linear equation, which is says here, this says y minus w is equal to 0. After this, I back to a system of linear equation. This can be written as this equation can be written here is as y is equal to w. So and just a minute, I am making mistake somewhere. Okay. So this can be written as x x plus x can be written as w plus z minus y, and yw plus z y is can be written as minus w. I'm making mistake now. Okay, let's see that what will happen. Okay, so this w can be cancelled out, so x is equal to z. So actually here is what's happening, two independent variable. What's the answer for this?
2 dimension is 2.
To find the dimension is okay. Dimension is okay. I'm right. Okay, I'm correcting. I'm doing correct. So now what we reach, that x is equal to z and y is equal to w. What it says that means it have two. Actually, when you system of linear equation, also you can conclude that this system of linear equation has two independent variables. Or after reducing it in reduced row echelon form, you will tell. So let me write the next step is that I am reducing it in reduced row echelon form, which is 1 0, and this is -1, and this is again, it will be what I'm doing, R2, sorry, R1 minus R2 I'm doing. Okay, so this can be written as 0 here, and this is 0, 1, 0, -1. Okay, so this says that, okay, in the reduced row echelon form, we will tell that this two are linearly independent. Let's say this is x, y, z, and w. So you can say it has this system of linear equation has two linearly independent, as here you are getting z and w.
So there are two independent vectors which can span this vector.
Yeah, that's the meaning. I'm actually trying to find those vector. I'm actually trying to find those vector. So let's say this z is equal to t and w is equal to t prime. So that means x will be t and y will be t prime, and z is t and w is t prime.
Yeah, there is a step that if there are two independent variables, we put one independent variable as 1 and second as 0, and then find out the vectors.
Yeah, correct. So let it 1 and 0. So final thing, x you will get 1, and z is y is equal to 0. The first thing is x will be 1, y is 0 here as here, and z is 1 again, and w is 0 again. Two independent. The second thing is put second one as 1 and this and first one as 0. So the first one you will get here again, x is 0 as here. Okay, 0, and next one is y1 is, sorry, y is 1 here, x, y, and z is again 0, and x, y, z, and w is 1 here. So you got two vector using this, as sir have did, hope you seen, if you seen in video. So you got a two vector. Now if you check, these two vectors are actually linearly independent. You can check easily. So when you do, it is equal to 0, 0, 0, 0, 0 vector, checking for linearly independent. So that means this is a comma b comma a comma b kind of a thing is happening, which is equal to 0, 0, 0. If you compare, you will get a is equal to 0, b is equal to 0. That means these two vectors are linearly independent. And if you see that these two vectors will actually span the whole vector space, this V. And actually this is the process to find a basis. So this is actually the basis of V. Now count the number. There are two vectors. So they'll be, so dimension of V is,
where is it covered? Is it covered under lecture or some tutorial that, you know, if there is an independent variable, I should consider one of those as 1, another as 0?
Actually,
No,
sir,
in this solve with us, there is step given there.
Acha, in solve with us guidance.
Yes.
As here you can see the steps also. Put as a 1 as a value and another one as a 0, and do the okay. And also in here you can see some in one tutorial in tutorial videos. Let me play it here. Okay, I in this video he is trying to find the basis of vector space which is in the matrix form. Okay, there are some other videos also in which he is trying to find the basis of vector space. So you will see that. So that's the process to do. Okay, as I here I did.
Yeah.
Continue. Can continue. Okay. So that means you that's the process you will try to find the basis for any. This is the best way. Actually, this is the very easy way to find. If you see the tutorials video, in the tutorials video I also did the same kind of process to find the basis. Try to find a system of linear equation and give it as a solve them, and try to find the independent variable and give as 1 0 and 0 1, and try then get the basis of that and count the number. That is the dimension.
Sir,
yeah, continue.
Sir, I am confused in finding the dimension in the matrix form, sir. That suppose, sir, I have a matrix of 1 cross 2. Then what is the dimension of that?
So let me tell you. Okay, I am taking the vector space, which is, see, the question is proper way to saying vector space, which is the collection of matrices of order 1 cross 2.
Belongs to R, sir.
Okay, belong in bracket R with
yes.
Usual addition and scalar multiplication as in matrix. This word will be added. Okay.
Yes.
What it in manner coordinate when entry wise addition and entry wise scalar multiplication. That's the meaning of usual addition and scalar multiplication. Okay. So now let's find the basis of this vector space. So let's take a general vector. General vector of this vector space 1 cross 2 means what will be in this form? It will be in the form of
X comma
1 row and 2 column. Here is A comma this form, right?
Yes.
This is the element of this
matrix 1 cross 2.
1 cross 2. Okay. Now just if you see in video, in tutorial video I have done in the 2 cross 2. Otherwise, let's see here. So let's take this A matrix, this one AB. Okay. Now put it, this matrix can be written as right like this, right? No?
Yes, sir.
What it mean that this is a vector of this M2 1 comma 0. Leave this one. Okay. Leave this here. This is also a vector of 1 cross 2. Okay. And actually, if you see that this is a linear combination A comma B of in this form, this says a linear combination. This matrix can be written as a linear combination of this one. I am giving a with a particular vector like 3 comma 5. I am taking a matrix here. Okay, 3 comma 5. So this linear combination in this form, these two vector 0 1 0 and 0 1, 3 1 0 plus 5 0, this matrix. So this says that these two matrices 1 0 and 0 1 will play a crucial role, and any vector, this says the any vector, this is a general vector, and this can written as here, see that can be written as A and B. So these two vector play a role here to saying that these two vector actually span whole vector space M1 cross 2.
Then the dimension is 2, sir.
So dimension is, now if you see that these are linearly independent. If you check that, the process is to checking as usual A time in matrix also the same.
Got it.
If you check that these two are linearly independent and say that, oh, this is a basis of M2 M cross 2 and the dimension of this is 2. Clear?
This is where I get a.
So can you take the example of 3 cross 3, sir?
I can take the example. Okay, somebody is asking here itself a doubt. Okay, can continue.
Yeah. So my point was that generally when we do about a vector space normal on a real line, so then it is bit easy, and that's how the whole tutorial and the lecture has been. That you start with a null set, and then you go for a maximal linear independent, or you start with the spanning and then you keep on reducing it. That concept is clear. But once it starts with a matrix, first I have to convert that matrix into decomposed one, which is like in terms of 1 and zeros, and then I go for this further analysis. Is that the first step that I have to do the moment it comes to matrix?
Actually, see, the reason is like operation is in matrix, it will never change. It will be entry wise addition, like it will be given most of the time entry wise addition, and like usual addition and scalar multiplication as in matrix. And the most probably do like this as here. I am taking a different example, maybe it will answer your question. I am taking a V as collection of matrices let's say I'm writing a matrix of order 2 cross 2, which is upper triangular matrix. Okay, collection of upper triangular matrix is actually is a vector space with respect to usual addition and scalar multiplication as in matrix. Okay, this is the collection of matrices, upper triangular matrices, upper triangular. Okay, upper triangular matrices, and this forms a vector space with usual addition and scalar multiplication as in matrix. So let's find the basis of this matrix. Okay, so take a general vector here. So general vector means entries are like any real number. General mean to say this one. So let's say upper triangular says so A, B,
0,
and C. Where A, B, C belongs to R. Any A, this is says as a general vector, saying to be a vector. This is a vector of this upper triangular, this V. This is an upper triangular. Now the very easy to, this matrix can be written as A time 1 0 0 0 plus B time 0 1 0 0 plus C time 0 0 0 1, right? So actually this gives the idea that these are also upper triangular matrix. This leaving to this, I'm saying this one, these matrices, right? And actually these are the element of this. These are the element of this V, and actually these are the vector, because you can see that these are also upper triangular, right? Upper triangular matrices. So actually these are the three vectors, and see, this is a general matrix, and you see that span, these are spanning, like spanning in these three matrices. So that means these three vector are span whole phi, this upper triangular matrix of order 2 cross 2. Now if you check that these vectors are linearly independent, if you check that 1 0 0 0 plus y time 0 1 0 0 plus z time 0 0 0 1, the process is same to checking the linearly independent, right? This will be equal to the zero matrix. Okay, because zero vector in this vector space is zero matrix. This is also upper triangular, you can see that, right? No matter the entries are all zero, but still zero matrix is an upper triangle. So if you check that, yeah, you will get x is equal to 0, y is equal to 0, and z is equal to 0 after this solving this expression and comparing. So that means these three vectors are independent and span the whole vector space, this upper triangular matrix. That means this is a basis. This collection of these vectors is a basis of that upper triangular matrix. Right? And count the number. The three vectors are there. So dimension of this vector space is 3. And this is the basis here below. Clear?
Yeah, thanks. That helps.
So for 3
and
cross,
also it will answer your, I hope. So same process. For
sir,
3
what
crosses,
is the
that's why I
dimension
am
of
going to
3 cross 3?
add the word. It will answer your 3 cross.
So what is the
Same
dimension?
thing. 3 cross 3 means will be matrix. So now tell me what will be the dimension. See, general matrix will be A, B, C, E, F, G, H, I,
Then sir,
J.
9. 9, sir.
So what will be the dimension? 9. Dimension will be 9 because 9 possibilities are there. 9 vectors can be, this matrix,
Sir,
general matrix can be.
I am a bit confused in sir rank and the dimension, sir. I suppose sir that the something is at pivot place, then it will be the dimension, sir.
Sir, just now I told you the differences about dimension. Please, you
Now
were
it's
there.
Thank you.
Very clearly I told you.
It's clear now.
So please clear
Yep, sir. It's clear.
time or almost everywhere you will see always the word dimension for vector space, rank for matrix. So this much the matrices also to find in the basis. And
Hello, sir.
Yeah.
Sir, can you scroll down the? Sir, okay. It is here, sir. You are saying that the dimension of the matrix is 3 cross 3 equal to 9. But sir, it is not always true. If it is a upper triangle or lower triangle matrix, but
So yeah, it will change because what in 3 cross 3 upper triangular matrix will be
sir, your voice is not clear.
It will be 6. Sir, your voice.
Oh yeah, sir, we cannot hear you.
clear now.
Sir.
Is it clear now?
No, sir, it's
Am I
not
audible?
clear now.
Hello, am I audible?
No, sir, no, sir.
No,
So
sir.
there's,
Am I
so we
audible?
can hear you, but there's still a bit of disturbance going on.
Is it clear now?
No,
No,
sir.
sir.
No, sir.
Is it clear now?
No, sir.
Sir, not, not.
Still not clear.
Am I audible right now?
Yes.
Yes, sir.
Okay, now I hope the voice is clear also, right?
Yes,
Yes,
sir.
sir. No.
Okay, no matter. So yes, okay. So I was discussing about, yeah, if the change, the condition is it is an upper triangular matrix, then your general matrix will be different, right? It will be 0 B C D E 0 0 F and up, right? This is the upper triangular. Now tell me what will be the dimension here?
6.
6.
Pick.
There are 6 non-zero vectors.
1, 2, 3, 4, 5, 6. Because there are 3 positive vector, 6 vector. Sorry. Yeah. So dimension will be 6.
Sir, I have one more doubt. Sir, here you are representing true cross true matrix M2R. And you are writing the element in linear combinations. So can we represent those elements in matrix form also?
No. Sorry, I didn't get it. Can you repeat again once more, please?
Sir, you are writing true cross true matrix vectors are linear combinations such that x on 0 0 can represent vector in matrix form.
It
I
can.
think the Gaussian elimination form.
No. So no. Matrix form.
The individual basis is already in matrix form, right?
No.
The
These
scalar.
are the vectors. These
Yeah,
are the vectors.
basis will
of
be in
M2R.
matrix form.
The individual vectors are matrix form only.
Vectors will be in matrix form.
So suppose the vector is not standard form, like other form like 3 cross 3 matrix. Yeah.
So yeah, actually,
so we will get many equations, sir.
I got your question. Actually, there is a possibility you may get a different vector also. See, this is a basis. That's why I'm wording a basis many times. Please note that a basis. There are another vectors. Maybe not only, it may be 1 1 0 1 and maybe different also. There are some which can span also, but that is also a basis. see, for a vector space, there are infinitely many bases, infinitely many bases. But dimension is unique. So this is a process to find a basis. There are many more different. Okay. Is it
Yes,
clear?
sir. Yes, sir. But when you
Am
will
I audible?
write, yes, sir. You're audible.
Actually, if you are able to write the linear combination in different form of the different matrix, that is also can be possible, right? This can those vector collect those vectors.
Sir, now because you are taking the vectors are so linearly independent, so you are directly saying that x, y, z is 0.
Yeah.
Suppose the vector are not linearly independent. The set of vector are linearly dependent. And we will get this 3 equation, more than 3 equation like x plus y plus z and so on. Then, sir, the vector we can represent it in a matrix form.
Okay. If suppose you are getting okay.
If it is not independent, then it is not a basis, right?
I'm not talking about basis.
No, he's still, I didn't, he's having some different question, but I am not reaching that. I'm not getting his question once. Okay.
Sir, vectors is not linearly independent.
Okay, correct. Okay.
And sir, find the linear combinations of the vectors. And sir, we'll get such equation like x plus y plus z something. We'll get many equations.
Okay. So yeah, actually then while solving, you have to form that, like you will get a system of linear equation in this form,
Yes,
right? Also, let's say I'm writing here one. Let's suppose you are able to write here in this form.
Yes.
Okay, 2 here, or let's say 1 here also. Like x plus y plus equal to 0, and x plus y again equal to 0, and the third one is y plus z is equal to 0. So these 3 equation you will find, right? While after the comparison, right? And
yes, sir,
now
but not linearly independent.
So not linearly independent, then those vectors can never be form a basis, right?
No, sir, I'm not talking about basis. I'm saying
Okay.
that can we represent in a matrix form?
Yes. Yes.
Actually, now you can write a system of linear equations in matrix form and do the actually you will try to find the, so you will try to find the solution. You will have
Can I represent those vectors like matrix form? They are already in a matrix form.
You have to write in the no. So matrices can never be written in the matrix form. Please be clear. So matrices can be never be written as a matrix form. Okay.
Yes, sir.
From the matrices, you will try to find some equation, and then those equation next step is
Take example of a 3x3 matrix M3 cross 3R.
Okay.
And those vectors are not linearly independent.
Okay, the vectors are not linearly. Okay, I'm taking 1, 1, 1, 1. Okay, 3 cross 3. Can you take a 2 cross 2? Will be easier. Will be okay.
So I think sir 3 cross 3 will be very clear.
That's why I'm saying or nothing. Okay. Let's take 3 cross 3. 1, 1, 1, 0, 1, 1, 1, 1, 0. Okay, or maybe more easier writing to be in this form. 1, 0, 1. Okay, 0, 0. Minus 1, 0, minus 1, 1, 0, 0, 0, 0, 0. Let's say here is 1 again, the same vectors I am writing with the first entries I have changed. Okay. Now I took 2 vectors. Okay. Next. So
sir,
these 2 vectors are linearly independent or not? You want to say, want to check? Okay. What's the question?
No, he's saying two dependent mean, not linearly independent. So you just
So
have to
take some linearly dependent vectors and make a linear combinations and find the value of the coefficients. Can we represent those coefficients in matrix form? So did you get my question?
Actually, when you try to solve those that system of linear equation, you have to change the using the coefficient. You have to find a matrix, right? Using as the Gauss elimination says, you have to find a matrix using those coefficient of the system of linear equation which you obtained.
I mean, sir, we'll get many equations.
Still you have to find. Yeah, you will get many equations. Correct.
So suppose the dimension of the m cross 3 equal to 9. So I hope we will get, I think, 9 equation, right?
Still you will get 9 equation. Yeah, that's okay. Okay, it's 9 equation. You have to find the matrix of that using that.
So 9 equations. For 9
using
equations,
9 equations. Yeah, correct.
Sir,
yeah,
is there
actually
any
correct.
different method?
No, Gauss is very easy to solve. Still you have 10
For
cross
9
10.
equation, it is not so easy.
See, so why you are worrying? See, if you understood the concept with 2 or 3, that's enough. Of 2 is enough also, and never will we ask in graded or quizzes like big do the big process. No, okay. So don't worry with that.
So only 2 cross 2 can come in graded
2,
or
3 cross 3 may also come. Will be easier form, right? It will no have to do like you have to go to 9 cross 9 kind of like 9 system of linear equation.
Sir, if it
There
is
will be
linearly
some trick
independent, then it
which
will
you
be
can
easy.
control.
But suppose it is not linearly independent, then it will be very lengthy.
Not independent, then?
Very lengthy, I think. We have to do many row operation there.
So surely there will be hint. If we don't want to be a calculation, right? This is maths too. So we don't want to. You only need to check your knowledge, not calculations. Okay, concepts.
Okay, sir. Okay.
So don't worry with that. Okay, so actually this is 7 o'clock from 4 to 7. So I hope many of I was trying to clear many of your doubts. I don't know. I I hope many of you got cleared your doubts. I don't know if you have doubt. You can continue. We can continue activity graded whatever you want, or we can end the session now. Also, that's the main I want to say.
Sir.
Okay.
So can you please look into this bonus practice activity? So until yesterday, we were not able to submit the activity bonus practice activity question. But since yesterday we can submit, but anyone who does it correctly is being awarded 75 marks out of 100, not 100%.
So
this is a new
I
issue
want
that
to
has...
say for you that I can only discuss your doubts. I am not going to discuss operational kind of queries like bonus or kind of. So don't. If you have a doubt with that question, I can discuss. But I'm not going to discuss why it's happening or those things. Okay.
So can you forward it to the concerned person?
Yeah, I can tell, or just write to in the discourse also and support also. I will say in both you should write, and then let's see.
Sir, is it
Sir,
possible to tell how to submit that one?
So
Sorry?
actually, we have been trying to, we have been writing to support as well as in discourse for 4 days since the activity was introduced, but we didn't get any response. Then we, yesterday we let sir know, and then sir resolved it yesterday. So I think people...
So maybe actually see sometimes needed to be the refresh more time, or like there are some process told you in the like please open incognito or do the refreshing and again please log in like such kind of things you need to do, because see somebodies are able to do and you are not able to do. That's the problem of internet or system. That's the happening, right?
Yes sir, but this problem is universal problem, and that's what I'm trying to say. So we have been writing in discourse and to the support team since the last 4 days, but no response. We were getting any response. Then we told sir yesterday. So he looked into it, and so now we can submit the activity, but now the evaluation, there is a problem in the evaluation of it. So it would be good if you look into it, because
Okay,
responses.
I will see, but if you are getting like 0 marks, so please wait. See, system is have recorded, like it will be recorded in that. Maybe because of some error, it's going to be your 0 marks. But please wait. Sometime it may be your, like, after some time it will be, you will get the marks for that. So maybe there may be a system problem. But yeah, you know that system can record the history and do the process. So don't worry with that. Exactly, like many times I've seen in discourse that you will submit, and after submitting that, when the assignment is over, many of you are starting posting, I got 0 marks, I
Yeah, this
submitted.
is this
No,
happens,
that
but this is,
after some days,
yeah,
maybe 1 or 2 days, it will, you will
yeah.
see the correct whatever your grades is that. So maybe because of that's happening. That's the main I want to say. Okay, so okay, leave it. I that's why I want to say I'm not going to discuss the operational kind of queries or like this kind of. So if you have doubt, specific doubt in a concept or activity, okay, we can. Otherwise, let's end the session, because that's reaches to be 3 hours. Okay,
Hello,
so
sir.
can we end the session?
Hello.
Hello.
Hello, sir. Yes, actually, I want to know that if two vectors are scalar multiple of each other, okay, then we say that in a R2 dimension, they lie on the same line, right? So,
Correct.
actually, I'm
If
not
you are
able to
lying
get
with the
that.
R2 and two vectors are in, okay, I am
Scalar
giving an
multiple of each
example.
other.
As you said,
Okay.
R2 is that, and I am saying 1 2 is a vector in R2 and 10 a vector in R2. So if you see that 1 2 can be, or 5 10 can be written as 1 2, this 5 10, sorry, 5 10 can be written as 5 times 1 2. So see that these two vectors, this one and this one, as here, are scalar multiplication of each other. So let's see in geometrically what's happening. So 1 2 will be proxy here somewhere. Okay, and 5 10 will be somewhere. 5 is maybe here and 10 will be here. So let's say 5 10 is that here. So okay, so pass the lines.
Yes, got right.
Pass so many lines from 1 2. So if you see that one line will be there which pass through these two lines. Sorry, these two vectors. There are so many lines can possible. Okay, but there will be a line which pass through these two vectors. That's the meaning of this is happening.
And also the origin also.
Clear?
Right. Including origin.
Okay.
Yeah.
So,
And
yeah.
so
also may not be, not necessary, may not be also.
Sorry, sir, but your voice is not continuous.
Okay, so
Okay.
So let's end the session. It's
The next
actually reaches 3 hours, but reach.
sir,
Is it clear? So I am ending
Yes.
actually the
Yes,
session.
yes. Yes,
So can I am going to end. Okay. Okay.
Yeah. Thank you.
Thank you, sir.
Thank you.
Thank you so much.
Thank you, sir.
Thank you,
sir. Thank you very much.
Can I ask in a later session?
Thank you, sir.